We are about to begin. Gaia. So, good morning, everyone. Welcome to Tenerife. Welcome to 16th Gaia Science Alerts Workshop. We now have time right to start 6 minutes later than planned, but that's Spain, so that's fine. We first will start with the welcome talks, and the first speaker of the day will be Valentin Martinez-Piet, the director of the IAC.
Thank you. Welcome everyone to that's me. Yes. Welcome to Tenerife. Welcome to rainy La Laguna. La Laguna is always rainy, so it's gonna be like this. I think the entire week. And about the clouds, we have Tate Observatory here on the island of Tenerife. Roque de los Muchachos, that's some of you might know, La Palma. I think you are going on Wednesday to Tate, and I believe this workshop has preference for islands, I've been told. This is number 16th. We do a total of 7 islands where we can practically, it's another one, but only 7 can you really make a workshop like this. So you're more than welcome to stay here on the Canary Island. You have a beautiful logo with the can, which is for the Canaries. But of course, our preference would be La Palma, where we have Roque de los Muchachos. Anyway, I've seen the agenda is fully packed. I think you're going to have a very interesting week. And there are a couple of talks that I have an interest and I might try to join you. I hope you enjoy. And as I said, welcome to Tenerife. Thank you.
Thank you very much. And the second speaker of today will be Pablo Redondo, who is our host here at IAC Tech, which is the building that we are here.
Good morning. Thank you for being here in this. So in case you are interested in visiting our facilities, feel free to come around and visit us. Well, the organizing committee will pay you for that. I think it's about technology more than science itself, but it's the technology that allows us to create more science. So we satellites, we do medical technology, imaging, we do optical communications, and large telescope is business as usual for the IAC. I'm quite jealous that you have a very good proportion of female to male here. You have 1,000, I counted 52, and 18 of you are girls, so this is very nice. The engineering team in IAC Tech is not so balanced because normally there are more boys and girls than in the field. But we are very happy that you are here. And in any case, we have a very pleasant week. I look forward to seeing you around visiting IAC Tech. Have a nice day.
Thank you very much. And once again, thanks for IAC and IAC Tech for hosting us here at Tenerife. And now we continue with welcome words from the chair of the workshop organizing committee, Łukasz Wycikowski.
Okay, welcome everyone. As it was said, it's 16th time we do it. So it shows that it is working, right? This kind of format and this kind of idea of workshops is continuing and it's thriving. Actually, this is the best, I don't know yet, but this is the biggest meeting so far. So let's make it the best as well. So there's some statistics, and thank you, Yara, for compiling this. So we're almost 100 people. So this is the biggest ever, as I said, from 27 countries and 5 continents, 59 institutions, 50 staff tenure, 17 postdocs, 13 PhDs, and 16 master and bachelor students, and there is 26 online participants. And I like to emphasize that we see the shift that people now prefer to meet in person instead of online, which is great. So that's what we're trying to do. But we keep doing it hybrid to increase the visibility and the accessibility of this workshop to everyone. So why we're here, right? So we're celebrating the 16th meeting in the series. But the main topic why we're here is the Gaia and particularly Gaia alerts. So Gaia has been observing for 11 years, but if you compare the number 11 to 16, it means we started way before Gaia started. So we were ahead of, we started with the workshops, we started preparing for what Gaia is going to bring way before Gaia was actually launched and started collecting any data. So Gaia has been observing, and now it's the over of the scientific mission. However, Gaia is still, data is being still analyzed. So it's gonna be with us for a long time. But the Gaia alerts has been the main theme of these workshops. That's why we started this way back in Cambridge in 2010. I remember my son was just 1 month old when we started. So in Cambridge, so he visited the workshop as well when the first workshop happened in Cambridge. So we're going to focus in this workshop on the scientific highlights and achievements of the Gaia mission, of course, but then with the focus on Gaia alerts, as that was the main theme. But also we will focus on the BH-Tom follow-up. That was the original idea of the workshop. We have Gaia alerts, but without the involvement of the community for the follow-up observations and then actually using the data, there is no point of doing such a great mission as Gaia and Gaia alerts. So hence we started encouraging the community to get involved, and hence these workshops. So we try to spread it away also from Gaia alerts. The last one was in January 2025. So there are no new Gaia alerts, but there is the Gaia alert data. But the sky is not silent, right? The sky is getting more and more active. Actually, the more surveys we have, there is a lot of sky surveys giving us interesting transients. But also we would like to shift away, not shift away, but also spread to not only to focus on transients, but also focus on what we call time domain astronomy. And if you think time domain astronomy is everything what changes, right? So transients, supernovae, it's like a kind of classical time domain. When people say time domain, they think transients, but that's not only it. Quasars, right? They are there. They keep changing. It's very interesting to trace the changes over decades sometimes, or minutes, right? So this is another time domain. Then you have stars doing weird things. Some of them, they get lensed, right? My favorite topic, but that's temporal. But some other stars, they occasionally get dimmer, right? This is also very interesting. And we don't know the timescales. We don't know where to look. And also asteroids, solar system objects, this is all time domain, right? So that's why we are here. We try to gather as broad scientific community as possible so that people start to see that there is a lot of commonalities, a lot of common things, especially in terms of the follow-up and telescope resources. This is what we can share coming from different science domains. Yet another aspect of this, why we are here, is the research and educational opportunities for these small telescopes. So we're trying to build this network of telescopes, and then apart from this amazing research we plan to do with them, there is also a huge educational value and outreach value of these telescopes, because many of them are operated not only by professionals, but by amateur observers and public institutions and schools. And pupils in school, they can actually do science. This is what we're trying to convey here and make it possible. So these are the many reasons why we are here. There is going to be a lot of different sessions. So we're going to have 41 contributions this is the very broad range of topics. So of course, Gaia and alerts. There's going to be a lot of talks related to BH-Tom and the follow-up observations, and topics like dimming stars, cataclysmic variables, young stellar objects, and others. There's of course going to be transients, quasars. We're also going to look into other surveys and outreach and how small telescopes are contributing here. On Friday, we're going to have a hackathon. I'll go back to that. And then the small telescopes and the solar system, that's the additional angle we're trying to spread into. And then we'll also have some talks about culture and geology during our visit. So we have a nice list of invited speakers. I will not go through them now, but you can have a look. It's a very broad list of fields we're trying to cover, right? So as I said, we're trying to be as interdisciplinary as possible in these workshops. Very often typically people meet at the conferences, very topical and focused ones. So we're trying to be not one of them, right? We're trying to bring people from different communities. And this is also expressed in the list of invited speakers. The workshop organizing committee, that's the name we're trying to use instead of scientific organizing committee, because WOC is a nice name. So this is the list of people involved at different levels, and particularly the people from this institute here and this island. They have been very active arranging. You can imagine how much work it is to arrange a venue, all the technicalities, posters, badges, and stuff like that. So I would like to express my thanks to this group of people. And so these are the people who are local, and they wear green badges, right? Green strings. And the people marked with asterisks, they can help you also if you don't know Spanish enough, if you need to communicate. And ombudsperson is Anna, if you need to talk about difficult things. There's a log table at the back, right? There's an email. If you need to email us, we've been bombarding you from this email, so you know this email already. Of course, funding, right? I have to mention this. So without funding, it wouldn't be possible to meet here. So primarily we are funded by the ACME European grant from National Center for Nuclear Research. And so this is the ACME workshop. That's why, hence the name is the ACME Time Domain Workshop. There is also a significant contribution from University of Warsaw, from La Caja Foundation, I hope I pronounced it well, and the venue and resources are provided by the IAC. There's also some contribution from European Astronomical Society of small telescopes. Last but not least, there is a very nice idea. You've seen this huge banner at the back. So you can take a picture of yourself with it. We will use it for pictures and so on. But also we would like to invite you to sign on it, right? There will be a pen provided. So you have the whole week to mark your signature. So I suggest you put your name and maybe your institution as well, so that then we can trace you back in 100 years' time or so. So I think that's all, right? I'll get back to the mic after Paul. This.
Good morning. Also a warm welcome from me. My name is Paul Beck. I'm one of the co-chairs together with Jaroslav and Lukasz. And I would like to fill you in some details on the local work. So we like to call it pre-flight, as we are ready for takeoff to the conference. So a few informations from the flight deck. First of all, the necessities. We have Wi-Fi connection, either with Ederoam, and you probably know how to connect, but we also have a Wi-Fi here in the ISC, and you see the password is ISC Tech with a capital I, 2019. It hasn't been updated, but it's working. We tested it. Also, there's an ISC guest network where you can simply sign up with your email address, and you have to renew it daily. You see power outlets at most of the desks of the tables, and some on the side. Experience has shown that there is always enough power for us to charge the notebooks. Plates and lunches will be served outside. You already saw one when coming in. We should not have food inside. Please eat it outside. And another thing, you might have seen the blue band. Please stay on this side, because there are cars coming in. We don't want you to get hit. The restroom is just outside between the two glass doors, on the next to the banner. There is a key, but please do not remove it. Otherwise, it might be difficult to lock or unlock again. On Wednesday, we are going to have a conference picture just before the coffee break outside. So if you want to be on the picture, please be here. Yeah. And there's an extra meeting room if you need for some teletrons or so that we have reserved for the full week, if you need it, please come see us at the log table in the back. For the speaker information, please upload your slides in timely manner, ideally at least before the coffee break of your session. Otherwise, our lovely log will search you and remind you of uploading them. You have the link in the email that was sent. You have several times received the link in the email. I think yesterday was the last one. But you also can find the link and the QR code for the Dropbox at the log table. So you can get the information there. This is a hybrid meeting. Please, and we have people listening from outside. Therefore, it's important to use the microphone when speaking and when asking a question. And when you're asking a question, we would like to ask you to start with your name and your affiliation, because people probably not from outside will not see you. So help them to identify who is asking a question. It's also a nice way of getting to know us. The session chair will give you warnings of several minutes. And if this is not enough, we brought some chairing tool, which is a traditional drum from Tenerife. And when you hear this sound, it's stop. So that I don't need that. Oh, I just got a sign. No. We have also the program available online because it's changing. It's a conference, it's a dynamical thing. It will change. So we have some printout versions at the log table, but and some copies, but they were on Friday. So changes have been applied. If you want to have the latest program, you can get it from the QR code, which is again available at the log table. Yeah, the log. So I would like to thank the whole team for pulling together this workshop. As Lukas said, it's a lot of work to do. And yeah, it was a community effort. You see us on the green lanyards, and we are happy to help you with basically whatever you need. So I'd like to mention that this is a safe space for science and people. We follow the ISC conduct, which basically excludes offensive language and sexual connotated language. Please follow that. Also respect your colleagues and also respect them by staying in time. And if you observe something, you can approach the whole log. And I would like to point out Anna, who is shown here, who is a trained ombudsperson for handling those cases and certified by the ACME. If you need any help, contact us or send us an email. Then there's the hackathon. We have reserved all the big meeting halls at the ISC, but people asked us if we really need them. So please, ideally by today, we have the major list, the main list to tell ISC what we need. And also there will be a meeting on Friday morning, a plenary session, but information will come in due time. And the link for signing up, again, is here on the QR code at the log table. If you need a certificate of participation, you can do that by filling out Google Sheet. And as you might have guessed, the QR code is available at the log table, so you don't need to follow right now and download it. There are a couple of activities planned. First of all, as Pablo Redondo already invited us, we're invited to come and see the ISC Tech Laboratories, a clean room where they develop next generation telescopes and satellites. And for the second half of the lunch break on Tuesday, we are invited to come. We have originally planned for one group of 20 people, but if there's more demand, we can organize for a second group of 20 people. Please come to a log table and put your name on the sheet. So we have a maximum capacity of 40 people. It's a first come, first serve basis. It's pretty exciting. We have done it. You will see everything from optical satellites to giant telescopes and the ELF project that Jeff is going to talk about. On Wednesday, we will have a cultural session, which will start as the last talk before lunch by Juan Antonio Belmonte, a colleague from the ISC, who has done research about the original inhabitants of Tenerife, which are hardly known, but they have done archaeological studies, even DNA studies to trace the origin. And it's a very exciting talk, and the whole lot is looking forward to hear it. So I hope you as well. And last year it was the most attended talk. Then we will have lunch. And if you have company persons, please bring them here. Let's have them lunch with us, because the bus is leaving at 2:30 sharp. From outside the ISC up to Tate. We will not have another stop. There at the ISC, at the observatory, which you see in the back, we will have a coffee break and then another geological information session keynote about the geology of Tenerife. Then we have a semi-organized walking tour through the observatory, but we will also visit a couple of telescopes, the Pyramid, Sun telescope, some other telescopes, and the ESA optical ground station. Then we wait until the sun goes down, because it's a tremendous view from the observatory to see the sun setting, and we will serve you a sip of wine with it. So it's to enjoy the moment. It's actually my students and I, we just did it last weekend, and they were pretty excited about it, so they're happy to go up again. On Thursday, we're going to have the conference dinner in Hotel Nevaria, where some of you are staying. It's a nice hotel in La Laguna, and it's important that you bring your badge, because here you have the voucher for the hotel, for the conference dinner, with your menu, a selection, and allergies. So first of all, please don't lose it until then, and then bring it and leave it on the table. With this, I thank you for your attention and hand back to the chair.
Good, you were in time, so I didn't need to use that because you were not giving that to me before your talk. So thank you very much. That's all from the welcome part, and now we can actually start the work, right? So we'll start with the science, and the very first speaker of the science session, you should stop sharing because this first talk will be online. Unfortunately, Johannes Salman, the Gaia project scientist, is online. He was not able to come to be here with us, but he accepted our invitation to actually start with the introduction to ESA Gaia mission, which I think that now, when Gaia is not observing anymore, is important to start with that. So now we see you.
Now, yes, and now I also unmuted. Hello, good morning, everyone.
Hear you, but we don't see your screen yet.
It's coming. Can you see it now?
Yes, now we can see that, and it looks good. So.
And you can hear me well, right?
Yes, yes. The
Okay.
stage or your chair in your office is yours.
Wonderful. Thank you very much. Good morning, everyone. My name is Johannes Salman. I'm the project scientist for the Gaia mission at the European Space Agency. I would like to thank the organizers for inviting me here. I would much have preferred to be with you there in person, but unfortunately that was not possible this time. So I hope to join this a future edition of the workshop in the future. So I will be talking about the Gaia mission. I'll give a broad overview. I'll give it the current status and then talk a bit about the next data release that we expect at the end of next year. But I want to start with the basic motivation for the mission, which is of the Gaia mission, which is to study the origin and the evolution of our galaxy, our home galaxy, the Milky Way. What you see on the right side here is the currently best visualization of our Milky Way as we would see it from outside the galaxy, a face-on map of the galaxies. You see the beautiful bar, the spiral arms, and our location here, the location of the sun that is pointed out in our galaxy. And so that's the goal really of Gaia. And how does Gaia achieve this goal? So first of all, Gaia measures the positions and distances to stars in our Milky Way. So that gives us the basic information about the structure of the galaxy. And Gaia is measuring this position not only once, but several times over the mission lifetime. And so we can measure the motions of these stars. That gives us access to the kinematics in our galaxy. And Gaia not only measures the distances and motions, but also the properties of the stars. So it determines stellar parameters, the compositions of stars for some stars, even their ages. And all of this together gives us access to the evolution of the galaxy. So it allows us to study the origin and evolution of the Milky Way. Gaia has three instruments, and it implements an all-sky survey with those. So we have an astrometric instrument, a photometric instrument, and a spectroscopic instrument. And of course, Gaia doesn't observe all the stars in the galaxy. We're observing roughly 1% of the stellar content of the Milky Way, and then we use those data to extrapolate to the entirety of the Milky Way. And there's lots of complementary science that I will come back later in the talk. The spacecraft itself is quite large. You see here on the left side, it's an image of myself standing on the full-scale model that we have at the European Space Astronomy Center here close to Madrid. The sun shield is 10 meters in diameter, and then you see the central part where the torus with the telescopes and the instruments is shown, which we see a technical drawing on the right side here. I will not go into the details, but you see here the focal plane, which has all the more than 100 detectors, optical detectors that for all the three instruments that I mentioned before. Gaia is a fully European mission. It was launched in December of 2013, and it operated from the Lagrange point L2 for 10.5 years of scientific observations. So that these observations finished earlier this year. I will come back to that. So as you see on the right side here is a cartoon which shows you how Gaia, the two field of view of Gaia, were sweeping across the sky. Gaia was constantly spinning and scanning the sky, and like that implementing this all-sky survey. Gaia observed anything that looks more or less like a star, so not only stars, but also galaxies, quasars, asteroids, and so on. Over a magnitude range of roughly in the optical from 3 to 21st or so. The data flow is classic, let's say. As long as Gaia was operational, it was sending its data to the ground stations, and then this raw data from the telescope, from the satellite, was distributed to a large consortium. There's more than 450 people all over Europe and beyond. So that's the DPAC consortium. That includes also significant ESA contributions. And so this consortium is then in charge of translating those raw data from the satellite into the catalogs of sources that you can freely access in the Gaia archive. So far, we have had 3 intermediate Gaia data releases, and I try to show this in this graph here. And I don't want to diminish Gaia data release 1, but it was the first one and the smallest one, and then you have that was in 2016. We have the second data release in 2018, and the so far biggest one, which was data release 3 in 2022. And so, as I try to show in this graphic here, is that every time we go through this iterative process, we have more data that goes into a data release. We have better data quality. We have a larger data volume. Also, the algorithms and the calibrations that go into the data release improve every time, and also the number and the detail that is included in those catalogs increases with time. So it's really an iterative process of incremental data releases, and that will continue over the next years. One particular aspect also is that there's no proprietary period on the science data for the Gaia collaboration, or actually for anyone else. So of course the Gaia collaboration has access to the data to produce the catalogs that will be then published, but there's no proprietary period on the scientific data, which is quite particular and very different from many other missions. I will not go into details of this of the other. There was an early data release 3 and the focus product release, but here these are really the major releases here. If we come to the current status of the mission, as I said, Gaia stopped taking science data in January this year. In this graphic here, you see a nice visual, and then you have around on the periphery you see some numbers associated to the mission. I'm sorry, did somebody say something? No, all good. I continue. So yes, so Gaia had a consumable on board, which was a cold gas that was used to maintain the attitude of Gaia accurately, which was necessary to collect sensible data. And so this cold gas ran out. So this was a planned that was unexpected, let's say. And so we finished taking scientific data on the 15th of January of this year. And here you see a summary of some numbers. So Gaia collected more than 3 trillion individual observations, so the 3 million individual observations. It spun around its axis more than 15,000 times. One number that I like to point out also, that we spent more than 50,000 hours in contact from our ground station with the satellites. So it's more than 12 hours per day that Gaia has been sending data down. I will come back to the publications, but another point also I want to point out here is this 580 million accesses of the Gaia catalog. So these are the accesses that access only the archives at ESA. So we also have partner data centers. So this number is not in there, but it shows that there's many people that use the data extensively, and it's a big effort as well that is put into there to make this data accessible and available to the public and to the scientific users. There was some noise in between, so please interrupt me if there's something that I need to take care of. Okay, so then after the end of the observations, Gaia went through a phase, a few months of technical tests. So this was to do some things that we couldn't do during the scientific missions, some special calibrations, some technology testing some components that were in space for 12 years, and looking into this basic angular variation, which is an instability of the spacecraft that was discovered early on in the mission. Gaia, as part of this test, also become much brighter, and what you see on the right side here is observation from a citizen astronomer that was taken from Spain, and you see here the apparent motion of the Gaia spacecraft relative to the background of stars. So we had a nice campaign here, which allowed citizen astronomers also to say goodbye to the mission in this way. And then finally, the Gaia spacecraft was put into its final orbit around the sun, which is displayed here in this figure, and then passivated, which is another word for permanently switching off at the end of March of this year. So it's now in a heliocentric orbit. You see, if you see my mouse, you see here's the Earth here, and then Gaia. So this is the situation in December of this year. So Gaia will be trailing the Earth, and then every 14 years, the Earth will catch up with Gaia, always in a safe distance. But as is written twice on this mission, on this slide here, this is not the end of the mission. So the mission goes on. We are now what ESA calls the post operations, and as Łukasz also alluded to, the next data releases are coming, and most of the people in the Gaia collaboration are working full speed and towards the next data releases. Gaia is an extremely productive science mission. What I'm showing on this graph here is we at ESA, for all our missions, for all our science missions, we count the refereed publications that are associated to a given mission, and this is the count for Gaia. So you see the first data release in 2016. That's when really things started to pick up. As a function of the year, you see here the number of publications per year. Data release 2, 2018, data release 3 in 2022, and you see that now we're reaching a plateau of roughly more than 2,000 refereed publications per year. So it's between 5 and 6 on any given calendar day. So it's extremely successful. Many people are making very good use of our data. We're very happy about that. So now it's really impossible to grasp the full depth and breadth of the science that is covered by Gaia. But I like to show this figure here, which is maintained by Michael Perriman, a former Gaia project scientist. It's the Gaia science tree. And you don't need to read all the small text, but essentially it shows you a tree. Again, all the Gaia science, you have branches that go off from the trunk of the tree, and then you see each of these little leaves is one small topic where Michael actually wrote a small essay on. So you can go there and click through them. It's quite instructive to see. But what I overplotted here is the broad categories. So you have, of course, the Milky Way, which is really the core science theme of Gaia. So that's a large fraction of the publications. You have stars, of course, stars, the main constituents that Gaia is studying. But Gaia is also doing lots of extragalactic science. There's lots of publications on catalogs and data, of course, technologies. Solar system objects, as I mentioned before, is a theme, and of course, exoplanets is a big field, and Gaia is also contributing there. So now I don't want to go into detail into many of those, but I thought I pick two results that are relevant for this audience. And so one is this one here, which I like a lot. It's recent, and it shows how Gaia also enables extragalactic science. As you all know, I believe in this meeting here, Gaia has been raising photometric alerts. So it's more than 27,000 that were collected until January of this year. And there are several talks which I point out here in this meeting about this. And so I show one example here on the right side. So that's as a function of time is the magnitude, and you see that this source here becomes brighter, and then you have this highlighted is when the alert was kicked off, and this alert here is part of three events. Actually, two were detected by Gaia, which is a new kind of transient, which is dubbed extreme nuclear transient. I point out the paper here that came out earlier, and so these events are thought to be caused by the tidal disruption of a high mass star essentially falling into a supermassive black hole. So here this was really powerful because Gaia has this very long time scale. So you see these are 10 years of photometric measurements, but also so long time scale, also very high precision monitoring of the sources, and that's essentially another way to find black holes in the early universe. I'll come back to this source later as well. And the other example I picked out is about exoplanets. Essentially, Gaia is not an exoplanet mission, but it actually detects exoplanets with all its instruments. So in astrometry, it has already found the signatures of many known planets. It has also already discovered a few planets. And with the radial velocity instrument, the same. We have for some planets with high radial velocity amplitudes, Gaia has been able to detect those. So WASP-18b is one of them. It's a very short period planet. And then in photometry, it has discovered two planets already through photometric transits. And then again, I want to highlight the photometric microlensing one. So again, on the right side, you see here that's from the paper from Wu et al. And you see here the magnitude of the light curve of this source, and you see the first data points here on the left. That's when the Gaia alert was triggered. And so all these follow-up observations then reveal this little blip here, which is the signature of the exoplanet in the lens system. So that's a very interesting system. It's a less than Jupiter mass planet in a 3-year orbit. And what's exciting about it is that it's so bright that it probably will be able to be followed up with radial velocity. So that's a nice prospect here. And I wanted to highlight this science result that comes out of the alert system. And there will be talks about this kind of studies by several other authors here in this meeting. All right, so looking forward now, as I said, the Gaia collaboration is already working hard on the next data release, Gaia Data Release 4. We will continue with this tendency, with this trend that I showed before. So now you see Gaia Dia 4 is the next big thing. It's planned for December of next year. It will cover the 5.5 years, the first 5.5 years of the data that Gaia has collected. It will be a big leap in the diversity and also quantity of data. So it will be 500 terabytes, whereas Data Release 3 is more like 10 terabytes or so. But we'll continue with the tradition. So it's science-ready, well-calibrated and validated data products. There will be extensive documentation. There's no change in the general approach to Gaia data releases, but we will have many new data products. I will come to that in a minute. And we expect a lot of new science from Data Release 4. So with a bit more detail, what I show here is on the right side, for example, is an example in the improvements that we expect for the proper motion. So you see here as a function of Gaia magnitude. On the y-axis, you see the uncertainty, the average uncertainty in the proper motion in one axis. And you see here the top curve is for Data Release 3 and the bottom curve is for Data Release 4. You see the massive improvement from one data release to the next, and that's not only due to more data, but also to the longer time span and to the better calibrations and algorithms that are being used. So we'll as usual, there's more than 2 billion sources. We will have many new data products, and for now also for the first time, mostly for the first time, we'll include lower level data, which also includes, for example, the CCD images that are underlying all the measurements that Gaia is making. We will publish the time series for the astrometric data, for the photometric data, so all the light curves. I believe Laurent and others later in this meeting will also talk about this kind of data. We publish essentially all the time series that we have of the radial velocities, the high and medium resolution spectra, many new data products. And so with all of this, both the better quality, the larger quantity, the larger diversity, we expect another explosion in terms of the science that Gaia DR4 will enable. We have a lot of resources here online. So you can see here, I point here out the landing page, which is the Gaia DR4 landing page. And there's one page that is already online, which is essentially the content, which is still incomplete, but we're updating it. So I show here just screenshots of the table. So it gives you a way to inspect what kind of products will we have in the archive for data release 4. And so you see here, these are the main catalogs, and there's a little search box up here. If you go to the website, you can look, for example, for new. So we have a column here, which is new in DR4. So this shows you what are the data products that are new in this release. It allows you to browse a bit and start to get ready for this next data release. As I mentioned, we are also going down in let's say what we call the data level. So here I search for data level 2. This is essentially the epoch data. So data level 1 is like image CCD pixel level data. Let's say the data level 2 is more at the individual measurements. Data level 3 is source based, so aggregated for a signal for a given source. That's what we mostly had in Gaia data release 3, and then we still have a data level 4, which is more like astrophysical parameters. A few previews. We already published this one here. So this was last year. We published the discovery of Gaia Black Hole 3, a very exciting discovery. I will not go into the science, but also there we published the individual astrometric measurements. So that's like a first preview of the kind of epoch astrometry that you can expect in data release 4, but not for one source, but for more than 2 billion sources. Again, coming back to the microlensing exoplanet that I showed earlier, so the astrometry that we will get in DR4 will be so accurate that we will be able to see the astrometric shifts in microlensing events. And so this is again from the same paper that I mentioned before. This is a simulation, so these are not real Gaia scans here in red, but this is a simulation of the two scenarios. So the blue curve and the black curve are different scenarios because there's some degeneracy in the photometric microlensing model, which can be broken by using the Gaia astrometry. This kind of approach has been shown by Jablonska and others. Many of you are in this meeting, and in this simulation, it's shown that with Gaia DR4 astrometry, we expect that this kind of events will then be able to be resolved with the epoch astrometry. So very exciting prospects to go deeper in microlensing and other studies. And the other preview that I wanted to show is this one here. That's the extreme nuclear transient event that I showed before. So here, what we did here was, this movie is courtesy by Simon Hodgkin, which I believe is in the audience. So what it shows here is the light curve on the left side, and on the right side it shows the Gaia spectrum. Well, it's uncalibrated pixel counts in the BP and RP spectrum. I will just show this, and I hope this comes out well on your side. But you see on the left side how the source becomes much brighter, and on the right side you see the spectrum. And I will just wait for it to play another time. So you see, as it becomes brighter, the spectrum, even here, even though this is uncalibrated, you can see how the spectrum changes. And so this reflects really the astrophysics. How does the event brighten the matter fall into the black hole, and at the same time the source spectrum changing. And then with Gaia DR4, you will have access to, of course, the photometry, but also all the individual spectra that are shown here. And then those will, of course, be calibrated. This is not public yet, but it will be public in a few days or so. All right, moving on. So even with data release 4, we are still not done. I'll continue with this graphic here. Once data release 4 is out, we will have many scientists enjoying those data, and then the Gaia collaboration will turn towards generating the 5th data release, which is then the legacy release, which will be all the 10.5 years of scientific data that Gaia has collected. It will be more than 1 petabyte in the archive, and this will then really be the end of the mission. So at this moment, then the mission will be dismantled from the ESA point of view, and Gaia will be in legacy. But this, of course, doesn't mean that the science will stop, because with Gaia DR5, you can imagine that what you can do with 5.5 years of data, but then you can imagine how much bigger, how much more you will be able to do with 10.5 years of data. I'm almost at the end here. I just wanted to point out a few resources for you. So we have general websites at ESA, which are more geared towards general public, which is the first one here, and where all the news releases that we make that regularly are given. Then we have the Cosmos pages, as we call them, which is really geared more towards the scientific community. So it's information for the Gaia science data users. So for you, if you need any information, that's the place to go. We also have an emailing list that we call the Gaia Bulletin. So I put the link here. So you are welcome to sign up, and we mail out roughly 4 or 5 times per year. We mail out the main news that are relevant for the data users. As I said, we at ESA, we also make news releases, and if you're about to publish any result based on Gaia data, and you are interested to possibly boost the visibility of that research, please reach out. We have some resources here, and we can help highlight your results. As usual, the reminder: if you use Gaia data in your publications, please acknowledge it. That always helps us. I also wanted to point out 2 programs, as you can get funding from ESA. So one is the Archival Research Visitor Program. So that's typically a few weeks long visits to 2 of the ESA centers. The next deadline is coming up at the 10th of November. So please have a look if you're interested in that. You can meet with mission experts or archive experts and optimize your research program. And the other program is the postdoctoral program of ESA, which is the research fellowships. The call just closed for this year, closed last week, but it's an annual call, and so in the 3rd quarter of next year we expect another call. All right, I come to my conclusion. So Gaia, although we have so far only published less than 1/3 of the data that Gaia collected, it already delivered on its promise to revolutionize our understanding of the Milky Way. It really changed the view we see our home galaxy. Gaia is now a backbone for modern astronomy and astrophysics, and I think also in this meeting we will see the large breadth of the science that the Gaia data spans. This year we are saying goodbye to the Gaia spacecraft, but as I said, the Gaia mission really continues strongly, and we have the 2 main data releases. They are still outstanding. The next data release is planned for December of next year, and that release, together with the legacy release, then will really unleash the full power of Gaia. So to finish, I just want to say that the best from Gaia is really ahead of us, and I'm looking forward to see all the fantastic results that you're obtaining with the data, and I'm looking forward to this workshop. So thank you very much.
Thank you very much. I'm not sure if you actually can hear the applause, so I will clap on the microphone. But there was an applause. So now we have time for questions. I remind everyone once again that if you're asking a question, you need to wait for a mic, because then, especially now, Johannes will not hear you at all. And please say your name and the institution. So, yeah, people are still in Spain, so we are waking up yet. I will ask because there is a huge change in the amount of data that Gaia DR4 will bring. So this actually requires, I guess, some changes in the hardware, no? At ESA.
Yes. That's correct. So there are several aspects, but yeah. So if we talk about database management, this is not my specialty. That as a disclaimer. But yes, the systems are being upgraded and are moving from to more modern database technologies, and to make sure that we can deliver the services that you're used to. Let's say in terms of speeds of archive queries and searches and so on. That we can also maintain that in the with data release 4. So absolutely, yes. With this larger amount of data, there come also changes of databases and technologies, hardware and software behind the scenes. Yes.
And is the same then foreseen for DR5, or this change will be okay for DR5?
Yes, I think it should be fine, because then from let's say from DR3 to DR4, we're talking about an order of magnitude, or maybe almost 2. Whereas from data release 4 to data release 5, it's a factor of 2. So that's better absorbable. Yes.
Okay, so now you know how to ask the question. I have shown you the example. So feel free to ask the question to Johannes. So no questions. So everything was clear, and everyone is apparently waiting for DR4. So we still need to wait a bit, but it's coming. We are all in DPAG working on that.
Very good. Well, thank you very much. And if there's any question, please write on the chat or in the Slack. I can answer them there.
There some question online, because that I cannot see from now. Okay.
Oh, I don't.
Okay. Thank you very much. And so it's again the applause that you cannot hear.
Thank you.
And now we still will continue with the Gaia as for a whole week. And now we will switch specifically to the variability part of the Gaia. And the next speaker will be Laurent Ayer, and he will be. So, yes, you can come. That's you.
There are 2 versions of your talk: version 1 and version 2. Version 2
should be called final.
Version 2. Okay.
So Laurent will talk about the work that CU7, especially the coordination unit 7, is doing, which is focused on variability. So I think it works. So the stage is yours. Oh, so this is, but you need to ask Łukasz how it works.
Next.
Okay. Okay, thank you very much for the invitation to talk here. That's a pleasure to be in Tenerife. So I will speak about a variable source with the Gaia mission. So not working. Okay, so the question is why Gaia is so remarkable. So that's my version. We heard the version of Johannes. There will be some overlap. First, it has an unprecedented astrometry. It gives position, parallaxes, and proper motions for so many stars with unprecedented astrometric precision. There are these 3 instruments on the same platform. This is also quite special. And these 3 instruments, they do quasi-simultaneous measurement. So when you do a variability analysis, it might be helpful that these measurements are nearly all these measurements are taken together. It forms a multi-epoch survey with a time series of photometry, spectrophotometry, and spectra. You have big numbers, as we saw with 3 trillion for DR3, that a bit less than 1 trillion CCD measurements. The baseline for the whole mission is 10 years and a half. So that means if you look at the precision of periodic objects, the frequency will be determined with a very high precision. You have a very high dynamical range. The brightest star in DR3 is 1.7 magnitude, and it goes to 21 mag. Also, the way Gaia is scanning the sky is determined, so that means you are able to compute the selection function. Gaia is in space, so it has many advantages, but one is that you can observe the whole sky that you cannot do really from Earth with one set of instruments. And then there is the aspect of the processing that you have cyclic improvements where you have better calibration, more data, better detection of outliers, and enhancements of problem identification. So globally, these different data releases, they try to go in diversity and also with better precision. So what is the result of the variable source in DR3? Globally, what we hit record, we publish the largest collection of variable source, of classified variable source covering the entire sky. We have 10.5 million, million missing, fortunately, variable sources, which subdivide into 9.5 million variable stars and 1 million AGN. And so we have the different types there of variables. In addition, because of a spurious effect, we were able to identify 2.5 million galaxies. The galaxies appeared to produce a variable signal in the G photometry. So it was quite amusing that from a defect, from a pollution, you can get something out of it. When you look at this variability tree, we see DR1 was focusing mostly on Cepheid and Hartley rays, DR2 on the spotted stars and long period variables, and also Delta Scuti stars. And then that's DR3. We covered a large number of variable objects. So how do we do this? Globally, that looks complicated, but in fact, it's very simple. We have data. We clean it, we extract some features, we apply machine learning, classical machine learning technique, and then you have also some human procedural approach with are deriving additional information. And so there is something a bit specific with respect to all our other large surveys. We are trying to merge machine learning technique on one side and, in a way, the way old astronomy was done, and with competent people who are specialists on certain field, sometimes very narrow fields. We try to derive completeness and contaminations, and when you look at the HR diagram, the color absolute magnitude diagram, we recognize, we see, yes. Here we don't see really the crystallization sequence in this, but you have the white dwarfs, you have the main sequence, the giant branch, asymptotic giant branch, the red clump. There the reddening is not corrected. And when you look about variable, it was done with a DR2 there. What do you see? You see this fraction of variables, which is for me an amazing diagram because you see the instability strip here with Delta Scuti gamma d'or. It's continuing, we don't see much, but with Hartley rays and Cepheids. You have also the ZZ clump. You see also here that you have more variables the further away, so that's for young stellar objects. So really it's of a richness which is remarkable. Now, if you look at the pulsating stars, you have the ZZT here. You have, yes, Cepheids, there, Hartley rays, and Delta Scuti stars. So you have really, when you merge the astrometry and the photometry and the classification, it's really unprecedented. Unfortunately, I could not include movies there, but there is also this diagram from DR2 where we see the motion of variables. So that was I think it was done a bit for Cepheid and Hartley, but it's the first time you can really do a movie of the motion of the variables in the HR diagram. And what you see that are usually bluer when they are brighter in a broadband filter. You have eclipsing binaries, which are often a bit more vertical, or if you look in detail, they have, for the algol type, they have two little branches, so like little hat. You have also Be stars, Gamma Cassiope stars, which are, when they are brighter, they are redder. So all this, obviously, all these signatures, you are able to define them thanks to Gaia, but it's also helpful to classify correctly the objects. You have also, it's a bit more difficult to see, but some Alpha Canum Venaticorum stars, they have a flatter distribution. They change in color, but they don't change in magnitude. So you have this movie, which is really, I think, baffling, at least for me. You have, Johannes showed this. There also, I could not play the movie, but you have an LPV and you have the RP spectrum. So you have the sequence of RP. And I think there we are facing a bit of a problem, I think, in the community, because you don't have, we are very accustomed with a time series of one dimension, of a magnitude, but we don't have so many methods to deal with time series of functions, which is varying. And I think there is a need to develop some techniques. We have also radial velocities. So we publish the largest data set ever of Cepheid and RR Lyrays with radial velocities. So you have the G band, beautiful curve, BP band, RP band, and here you have the radial velocity of these objects. The photometry, you can also derive of RR Lyrays and the special shape of the curve. You can derive the metallicity. That was a beautiful result of DR3, and where you have the LMC, which is more metal or more metal rich than SMC, for example, and you have this distribution. It's really nice. You have also Sagittarius stream here, galaxy. And when you look at period and amplitude as function of metallicity derived from the photometry, you have also this effect. I think these diagrams, for the people who worked on the domain for years, it's amazing. That's really a revolution. We had also the largest data set of radial velocity for long period variables, so 9,000 stars, and suddenly you can see better when the period of photometry, if that's truly a pulsating star or not. So you can do many different things. But small is also beautiful. I showed large variations and large variability like LPV, Cepheid, and RR Lyrays, but also small is beautiful. And here I present always this slide in conferences because I love this slide. And it's about exoplanet in transit. I'm from Geneva, and so the people in Geneva, they are specialized. Many people are specialized in exoplanet, and some members of the exoplanet group, when I said, okay, we will look for transit in Gaia data, I think on one, he told me, you will find 0 with Gaia. I was baffled. When you look at the precision, the sampling, I was sure. And so in DR3, we had 214 candidates. 173 are known already, and 41 were new systems. And we observed 2, and the best cases, and they were confirmed. So we had two exoplanetary transits, 2 exoplanets discovered by transit method with Gaia data. And we can see that the 39 others, they are still very, very good candidates. I was surprised that the people, they didn't dig. Probably they were a bit traumatized by Hipparcos, because in Hipparcos mission, there was a search for exoplanetary transits, and they devoted a lot of time observing those and with 0 result. But with Gaia, it's a totally different game. Also, there is a collaboration with a test mission And with cycle 3 data with DR3, we were able to confirm 5% of the test candidate. So saying, okay, we see a signal also at the correct period and there is a little dip. And 5% are background eclipsing binaries. So Gaia can help us to distinguish between contamination and a true transit. And now with the cycle 4 data, we are more at 30%. We are able to give an information for 30% of the cases of tests. Also, we see some surprises that was done by Connie Hart, where we see we can go in very tiny amplitudes. So you take some Kepler stars, and then you look at the amplitude in Gaia, and we see that we can reach 2 millimag in RP. It was a big surprise for me. So that means for DR4, DR5, we can imagine that we would be able to detect millimag variability for stars. Also, there is another surprise, is that the sampling of Gaia is obviously nothing to compare to Kepler or TESS. It's sparse, but still we were able to detect multi-periodic behavior. So, for example, here you have the Kepler data, one star with 2 frequencies, and that's Gaia data, which detected correctly these 2 frequencies. Okay, when you look at the precision and the sequence of the precision, you have as function of the magnitude, you have the mean G magnitude uncertainty. This is, I guess, DR1, DR2, DR3, DR4. And you see that there is an improvement. So that's exactly what I was saying, is that through this iterative processing, we improve things. People could argue, yes, sure, because you have more measurements, so the mean, you gain the square root of n. You double the number of measurements, so you lower your, but it's not only this. If now you look at the individual, not the mean magnitude uncertainty, where you look at the field of view G uncertainty, this is DR1, DR2, DR3, and DR4. So that means really we improve these calibrations, and that's the advantage to have this iterative approach. Now I will go to several other subjects, the period luminosity relation. So we produced the beautiful period luminosity relation of delta Scuti stars. That was a surprise that it is so nice. And all you see there is this luminosity with the Cepheids. This was with Hipparcos. So when I show this in conferences with amateur astronomers or the public, I say, okay, the people, they believe there is a relation, linear relation. For me, I was coming from theoretical physics. I looked at this, it's a cloud of points. But that was with Hipparcos. This is DR1, DR2, and DR3. And so you see that there is not only amazing improvement of the astrometry, you have also many more stars. So you have many more, we detected many Cepheids. In microlensing, another topic dear to the heart of Łukasz. So by merging the astrometry and photometry, you can lift generacies, and that's what will happen for DR4, where we will be able to have a full description of the lensing event. Also, the classification is in improvement. We have new features, new attributes of the source. We improve, although we have a struggle currently a bit we improve the training sets. And so in quality and in number, we had to separate a bit the analysis in primary and secondary sources, but it's more kind of perturbation there, but we try to improve this it's making distinction between these primary and secondaries. We introduce also an anonymous class, so that's helped to channel some sources in something which we don't really know. And we also are tuning the hyperparameters. So just we had these fantastic results of in the literature from Johannes. We have 2,000 per year. I was a bit curious, how many are connected to the statistics is done differently. How many are related to variability? How many are citing the articles we produce in DR3 and DR2? And so we see we reach 300 citations per year. This is an estimation. So we are not at the level of 1 per day, but not far. And I looked at 30 for this year in 2025. And we see there, what are they concerning? The search of variables. So we see there is on the local group many papers on RR-Lyrae stars and Cepheids. There is also RR-Lyrae in the halo. We have also cluster analysis with eclipsing binaries and variables. Binaries, even though that sometimes the people are not citing, I realize that people are very bad at citing. So I think that's this case. Maybe I'm mixing up, but they cite the result on astrometric binaries, and the paper they cite is on eclipsing binaries. So the people are a bit not so good sometimes in the citation. I hope the paper is better, so I didn't read the full paper there. There is also an activity on X-ray counterpart, young stellar objects, black holes and dark companions. So we see there is a variety for many reasons they cite the work. There is a determination of astrophysical parameters. There are several papers on metallicity and rotation periods. Obviously, the parasitic relation is something fundamental where Gaia is contributing. And I was a bit sad to see that they used our paper to exclude source. So there were, yes, 1, 2, 3, 4, 5, 6 papers were using the citers for saying, okay, this source, we don't care. We remove them from the sample. So that was quite amusing. And there is also comparison with other surveys. So we see that the usage of this time domain photometry of Gaia is used in many, many different applications. In preparation, now we go in preparation of DR5 minutes, okay. We are doing some deep learning approach with autoencoders. So we have a light curve and we have encoder limiting to 5 latent variables, and we decode and we reproduce the light curve. The system is trained to do this. One of the pioneering work on this approach of images of light curve was done by Wukash, but with a classical neural network, I guess. And we do this with so the light curve spectra and the DMDT method, where we form all the couple of time difference and magnitude difference. And then we add other fundamental parameters, and we train the system and reduce to 2 dimensions. And you see that globally it's working. So this will be published in DR3, this method, and it can have several applications for the anomaly detection, neighbor search, clustering, classification. So I think there that will be quite interesting to see, and probably the community will develop other such method. Another topic which is dear to my heart is the white dwarf. So what do we do there? We looked at the standard deviation as function of the mean magnitude, and we take a threshold and we take all stars which are higher than a certain limit. we plot these stars for the white dwarfs, and we see that there is a series of clumps. We see also another clump here, a little branch here. So we see there are substructures. I think there, I've shown this already several years ago, maybe in 2020, and there was not much reaction. But I think there is a lot of potential which is underexploited. Now, if you look at the frequency, what we did, we took ZTF data and we look period search if that's coherent in the two bands. Then the size of the point is the frequency. Bigger is higher frequency. And we see ZZCT clump, V77 Hercules stars. We have one example, but it's spot on there. And we have different things. And we also, the color is the ratio between the B and R amplitude. So we then applied unsupervised classification, and you see the different classes. So we see that on the variability of white dwarf, Gaia should be quite amazing there. The community didn't realize that I think yet, and there will be probably many studies. I finish here by also mentioning a Gaia Science project, Gaia Citizen Science project. And I think it's important to merge machine learning technique with expert astronomer and citizen scientist. And what we do here, we have the light curve, we have the folded curve with a period, the motion in the HR diagram. We see a nice loop there, and the position in the Milky Way. And so this, we ask them to classify. I think we had several campaigns, and it's extremely interesting. I had a lot of joy just answering comments and understanding a bit better. Visualization, I think there is a strong message. With so many data, the people I got often criticized in the community to say, when I was saying, okay, I want to visualize subsamples and things, people, they have billions of stars, they have a black box, they have results, and they believe in the results often because they look at statistics, but to go through individual sources and check subsample is fundamental. So for this, I will conclude, but the conclusion will be very simple. I think Gaia is truly remarkable.
The conclusions were shorter than I expected. So now we have plenty of time for questions. What DR4 is bringing us.
Yes, maybe just a comment in DR4. We are in the really processing the data. We processed nearly 20 million, and I didn't want to show some example because it's a bit, we don't know exactly, it's difficult to define exactly what we will find.
So how many variable classes?
How many we should be above? Well, maybe if we include subclasses, maybe 100.
So now it's up to...
There is a question there.
Thank you for your talk. Edita Stonkute, Vilnius University. I was curious about those exoplanets that you mentioned, especially the new ones or candidates. Are you following the rest ones that you mentioned, 39 or so?
No, the 39. So globally, what we wanted to do is when we had these candidates, we were obviously not sure that they were good, and we wanted to demonstrate that it is working. As I said, there was a bit of a trauma with Hipparcos and people who followed that with radial velocities. And globally, we show it's working. We didn't follow these 39 sources, but now will come DR4, and we will see if these 39 sources will be confirmed. My personal opinion is yes, probably. And then there will be many others. And so obviously with having the higher photometric precision, more data, globally the threshold of size of exoplanet will go down. It will be globally what we have here is Jupiter-like. So globally we probably will go a bit smaller. So for the moment, there is no, from our side, and it's not our mandate in a way. In the consortium, we demonstrated it's working, that some our results are really solid, there is no doubt, and that's it.
And what is your personal number of exoplanets that actually Gaia last release can show us?
So globally, obviously, the strong aspect is with the astrometry. And there, I'm not sure there were public announcement. And to tell the truth, on my side, I don't know. Michel Mayor, last week, he gave a public conference and he tried to inquire to me how many there will be from astrometry. And on my side, I don't know. So it's very simple, but probably there will be many. We saw that there is the one of Stephenson. There was another. So globally, there are from the article of Hall, there are already 2 astrometric which were confirmed, but there will be many, I guess.
Thank you. And about the project for community that you mentioned in your last slides, it's still available?
Yes, it's still online, and we see that people are contributing. So during the real official campaign, I was reading, I think many comments. I was replying to some. And since it's not official, I'm not checking much. We were several, Milena also, and we were a group looking at these. But I think it was a really good experience, and I think the citizen scientists, several liked it very much. I think that we received extremely good comments, and as a scientist, I loved it as well. So. And there will be, I'm sure there will be campaigns for the cycle for DR4 data.
Okay, we still have some time for questions.
David Buckley from the South African Astronomical Observatory. I'm interested in your white dwarf color magnitude diagram, and you're identifying some white dwarf, red dwarf detached binaries, presumably. Can you say how you know that they do contain a red dwarf? And can you also say why you don't expect, why you're not seeing much redder colors, ones that are filling in the white dwarf sequence to the main sequence?
Yes, so there that was because we based our study from Gentile Fusio, and he introduced a cut to select white dwarfs, and so that is why we don't have the other. Obviously, for the first question, you have these stars which are between the white dwarf sequence. They have the kind of the right color ratio between BPRP for being a binary system. And so that was the conclusion. That's why also we tried to apply this unsupervised classification to see in the data, do they separate? And they separated. But in fact, there should be, so that's a very good point, because globally, what should be done is that we should extend this Gentile Fusio to near the main sequence to have a full population. That would be very interesting. but we have to limit the scope of this work, and to start from this catalog of Gentile Fusio was the easiest.
Okay, I think one final short question, if there is one. And if not, Laurent is here, so there is plenty of time during lunches and coffee breaks. We planned that on purpose to be long enough for discussions. So thank you very much again. And now we continue with Ana Escorza with a time domain which is still a bit beyond Gaia's reach.
Thank you. Okay, hello everyone. My name is Ana Escorza. I am based here in Tenerife, and I'm one of those people that you can call for help if something goes wrong or if you need a tip for a bar or a restaurant this week. But now I remove my organization hat and I put the scientist hat. And after hearing how remarkable Gaia is, I came here to show you a few things that Gaia cannot do on its own. Particularly, I'm interested in long period binaries, like very long period binaries. And I want to convince you that they are crucial to understand some problems that we have in the low and intermediate mass star regime. And this is an example here. So I work with systems that are post-interaction, but still very long periods, and that they all have gone through a formation scenario like this one that I'm showing you here. We have a binary system, main sequence star, and one of the stars evolved all the way to the AGB phase. And at that stage, it transfers mass to a companion. This companion, if the mass transfer happens at the very end of the AGB phase, will be polluted with the products of AGB nucleosynthesis. So we will have carbon and S process on the companion star. Evolution continues, the AGB star disappears, becomes a white dwarf that we can barely see, not even in the UV in some cases, and the primary star becomes this polluted star that I am studying. So why do we care about these objects, and why it's important for me to make the point that for this type of science, Gaia is still not enough on its own, is that these stars keep track of the nucleosynthesis of AGB stars, but in atmospheres that are much more simple to analyze. So we can learn about AGB nucleosynthesis analyzing main sequence stars of red giants, which are easier to deal with. Additionally, the orbits of these post-interaction systems are going to teach us how AGB stars or red giants in general interact with companions, something that, if you ask me, is one of the most important problems that we have not solved concerning low and intermediate mass stars. To illustrate this problem, I show you here the eccentricity period diagram of some of these systems. So all the families plotted here, they have different names, but they are just because they appear at different metallicities, different evolutionary stages, different environments, but they are all stars that went through this evolutionary channel. And at some point, an AGB star interacted with a companion and polluted this companion with this process. So all these family of systems occupy the similar region in the eccentricity period diagram. And as you can see, they reach periods up to 10,000 days or more. Why is this problematic for low and intermediate mass binaries? Is that if we use standard binary evolution models to try to reproduce these orbits, we get two different interaction channels that these stars can form through, right? We can form them via Roche overflow, so we can have the AGB star fill its Roche load. And then we expect very short and mostly circular orbits. On the other hand, if the orbit is initially longer and and the pollution takes place via wind mass transfer, we expect longer orbits that are eccentric only from around 3,000 days. The fact that we cannot reproduce these orbits at all is a problem. This is a bit of a dramatic view. There's been some proposals, some mechanisms that can alleviate some of these problems, but right now these orbits are not reproduced. If we study these objects using Gaia, we will see this. So we cannot even reach to see that there is a problem here. What do we do then? Well, we can rely on long-term monitoring programs for radial velocities, but still we need decades of data to fit an orbit. The Hermes spectrograph on the Mercator telescope in La Palma has been monitoring these evolved binaries for a long time, more than a decade now. But still, for some of these systems, 1 decade is just one orbit. So it's still not enough. We have combined this radial velocity data with archival data. They are the best known ones are bright, so they've been observed before, so we can mix different radial velocity monitoring programs, but still these orbits are long. Additionally, relying only on radial velocities has one more problem. The main character of these systems right now is the red giant or main sequence stars that is the primary of the system and that is polluted. But we are trying to learn about AGV nucleosynthesis and about the interactions in these binary systems. And for that, we need to learn about the white dwarf as well, the invisible companion, because that's the one that did the job, right? That's the one that processed the nucleosynthesis elements that we are interested in. If we rely only on radial velocities, we can work with the famous mass function equation, and we can use the periods, the eccentricities, and the semi-amplitudes that we measure to get this value. The primary mass, the M1, we can get it evolutionarily put in the star on an HR diagram, for example. But if we want information about the faint companion, we still have this annoying inclination factor. And it's like, well, we discarded Gaia at the beginning because it was not enough, and Gaia can give us these inclinations, right? So we need to bring it back, because the idea of these talks was showing you what Gaia cannot do alone, but showing you as well how powerful it is when we combine it with additional data. Unfortunately, these orbits were not seen for Gaia alone, but fortunately, Gaia had an older brother that also looked at some of these stars. And when combining Hipparchus and Gaia is when we can truly do astrometric magic for these long period binaries. You may have heard about this concept, but in case you haven't, I will introduce it quick. We can define three proper motions using these two missions, right? We can define the proper motion that Hipparchus measured a few decades ago, and the proper motion that Gaia is releasing every data release. And we can define a third proper motion that is the one that we calculate by using the positions of these stars between Hipparchus and Gaia and the time that has passed. If your star is single and is just moving through the galaxy doing its thing by itself, these three numbers should be the same. However, if we have a binary system, even if we don't see the companion, the movement of the primary star around the companion is going to change this value. And we can define a proper motion anomaly as the difference between each one of the Gaia or Hipparchus proper motions with respect to this long-term one. These values have been collected by Timothy Brandt in the Hipparchus Gaia catalog of accelerations, and that can be queried and used and combined with your radial velocity data or with your interferometric data or with whatever data you have to add this long time baseline to your binary analysis. So combining the radial velocity data that I already showed you and the astrometric data from Hipparchus and Gaia is the way that we can actually learn about these systems as a whole. So I'm going to show you an example from one of those dots that I had in the eccentricity period diagram. This is a barium star, so a star polluted by an AGV star in the past. I think it is in the main sequence, but I don't remember. Well, it doesn't matter if it's a main sequence or a giant star. It's a barium star. And the period is about 40 years, as you can see here. We have a lot of radial velocity data for this star, but only with the radial velocity data, we could not fully constrain the orbit. However, fitting one Keplerian model to the radial velocity and the proper motions of both Hipparchus and Gaia, we could constrain the period and the inclination of the system, getting access to the mass of the invisible white dwarf as well. We also use the Hipparchus epoch astrometry, but for these long periods is not super meaningful in most cases. But it helps you with the orbit on the sky. So this specific star has a white dwarf companion that is 0.94 solar masses, more or less. We did this for as many targets as Hipparchus saw, because obviously we cannot use the Hipparchus Gaia catalog of accelerations unless Hipparchus saw your favorite target as well. This was done using Orvara, which is an open source code also developed by Timothy Brandt. It uses MCMC to find the best fitting Keplerian model to all these data, and it uses as priors the mass of the primary, so you still need the evolutionary mass, and the Gaia parallax. So, But I'm sure that there are other codes there that use different different setups in case something is more interesting for you. Just a couple of extra examples where we could apply this for different long period binaries. We also discovered a neutron star candidate accompanying a red giant in the system 56 Ursa Majoris, so very close by. If we can prove that is a neutron star, that will be a nice discovery close by. We also applied it to AGB binaries themselves. We were trying to work with the progeny of AGB binaries because AGBs and AGB binaries are very complicated. But when you combine radial velocity and astrometry, the fact that you are using the direction on the line of sight and the direction of the sky, it adds some constraints that allows you to remove some uncertainties, and it's easier to deal with. So we have done it with AGB binaries as well. And finally, since radial velocities will prove your shorter periods better, and the long proper motion anomaly will prove your longer periods better, we could also identify two triple systems with a short orbit and a very, very long orbit outside. We had access to the masses of the components as well, thanks to the combination of the RVs and the astrometry. And we could say that the Y dwarf in the two systems is outside. So these targets are very interesting to study tertiary mass transfer in binary systems as well, in triple systems in this case. So this is all what I wanted to tell you. Basically, we've used the mass function equation and we've plugged in numbers there. The radial velocities, we still need long-term radial velocity programs for these systems, evolutionary masses for the primary star, but the Hipparchus Gaia catalog of accelerations is a gold mine if your favorite system is a long period binary and Hipparchosoid. So it needs to be bright enough as well. Or we can keep funding Gaia missions so that we can keep doing this for longer. And these are just a few take-home messages, both from the side of the science. So AGB interaction products are important to understand how big convective stars interact with their companions. But such orbits are inaccessible by Gaia alone, and we need a lot of data of different kinds. And the more data types that we combine, the better we are going to understand these systems. And finally, yeah, the Hipparchus Gaia catalog of accelerations is incredible if your favorite target is very long period binary. So if you have questions about it or want to exploit it, please reach out. And that's it from me.
Thank you very much. Now we have time for questions. So Milena, co-chair is running.
Thank you, Milena Tajczak, Warsaw Observatory. Thank you for a very nice overview. I was wondering, since some of your systems, I know there are long periods, but they also have, some of them have high eccentricity. Is there a way that there are at periastron close to each other so much that you can see some effects of some kind of tidal interaction between those stars, both in the light curves or radial velocity, or is it they are too far away?
I think they are still too far away. When the Y dwarf was an AGB star, if the orbits were similar to this, probably yes, because the AGBs are huge. But right now, I think they are too far away for just the main sequence and a Y dwarf to see something like this. Thanks.
Hi, thanks. A really nice talk. Simon Hodgkin, Cambridge University. This is not a well thought out question at all. It's a rambling question. But it occurs to me, you actually have 3 epochs of proper motion measurement from Gaia, not solely from DR3, but you have one from DR1, DR2, DR3. And for an object in an eccentric orbit, if you catch it at the right moment, you might actually see that evolution catch the eccentricity. And I wondered if you exploit the DR1, 2, 3 proper motions, or you're just using a single epoch.
Yeah, so I have not explored the 3 together, but because I directly use the Hipparchus Gaia catalog of accelerations as it was given to me. But there are 2 versions of it, one for DR2 and one for DR3. And what we did was comparing if the results changed much. And there was no big difference between using the Gaia DR2 and the Gaia DR3 results, but I've not compared them. Yeah. Yeah, the microphone.
Follow-up question. What is the favored mechanism for giving you your short period high eccentric systems? Does it involve a third body or?
My personal favorites, I change depending on who I talk to. So, for example, the idea that roach lobe overflow with red giants is less unstable than the way it's treated in classical models is it's a good one. Instead of adding third bodies or disks that can pump up to your eccentricity, simply the fact that we don't know the physics as well as we think we know. So I know there are several groups working on the stability of roach lobe overflow, and I think that can fix the low period part of the diagram. For the longer ones, I think we need some kind of eccentricity pumping mechanism could be because of the way the mass is transferred, the angular momentum is lost, or it could be a disk that forms during the post-AGB phase. A lot of post-AGB binaries show disks, so it could be the disk as well. Third bodies in some of them, but I don't think triples will solve the whole thing because of numbers. But yeah, it depends on the area of the diagram. I think we need to invoke different magic to solve it, yeah. Thanks.
Good answer. I like the stability because my stars has the same problem.
Yeah.
So one final quick question, Nada?
Hi, Nada Ikenets, Isaac Newton Group of Telescopes. I might have a naive question. So how do you even find these candidates or targets since the period is so long? I mean, how do you know that it's actually periodic and it's not just a star normally,
Yeah, they are flagged because of the chemistry. So at some point, someone notices that in a main sequence star or a red giant star has the process of nucleosynthesis of stars that are much more evolved, in this case, the AGB. And then you assume that the chemistry is telling you that it's a binary and you start monitoring until you get bored or detect binarity.
Okay,
so
thanks.
Okay, the rest of the discussion, we move for lunch.
Yep.
So thank you again.
Thank you.
And we will continue with something completely different, which actually shows how Gaia is powerful, because this will be Gaia-related talk. It will be about anomalous stellar rotation by Diego Godoy Rivera, but it's completely different from what we heard until now. So, Diego, the stage is yours.
All right, thank you so much. Let me start my timer. Okay, good. So, hello everyone. My name is Diego Godoy Rivera. I am a postdoctoral fellow here at the IAC in Tenerife. I am also wearing one of the green lanyards, so you can come to me for help. But now, let's go to my presentation. So my talk is about clues to anomalous stellar rotation from the Gaia photometry, or particularly how the chromatic information from Gaia can help us solve this mystery. So we had a few talks about this already, but Gaia has really revolutionized astrophysics. And at least for me, when I first think of Gaia, I think about parallaxes that can be turned into distances, and also about photometry, but usually just the mean photometry in the G, BP, and RP passbands. So using this information, we can construct exquisite, and I really mean exquisite, color magnitude diagrams. In this case, I am showing for a stellar population, the stars observed by the Kepler mission, the Gaia, so absolute G-band magnitude on the y-axis versus Gaia BP minus RP color on the x-axis. Those are for the observers. For the theorists, you have luminosity and temperature with some representative values. But however, the power of Gaia does not stop here. As we heard in a few talks already, we can also have photometric variability information. So Gaia has completely changed the game in this sense by providing time series photometry, but also the classifications. Gaia provides numerous classifications. Here I'm showing you a subset of those. I don't expect you really to read them because there are so many of them, but this can really complement the color magnitude diagram or CMD information. So let's take again the population of stars observed by the Kepler mission. Here I am showing now the histogram of how many targets were classified by Gaia in the Kepler field in each of these categories, and then we can map these variability classifications back onto the CMD. So for example, solar-like stars is the most numerous categories. We have here up on the upper right of the CMD, long period variables. We also have, some cataclysmic variables, white dwarf, basically everything that you could want. So Gaia is, of course, not alone in terms of reporting amazing light curves. And of course, there are missions that are dedicated to this, typically observing in white filters. In this particular project, I am working with the stars observed by the Kepler mission. So just for context, Kepler observed the same field of view of stars that I'm showing you on the right for about 4 years, continuously, from 2009 to 2013. So Kepler observed about 200,000 targets, and from these amazing light curves, people have done, of course, a lot of work. But just to highlight a few, about 3,000 exoplanets have been discovered via the transit method. Asteroseismic oscillations have been detected in over 15,000 stars. And particularly important for this, stellar rotation periods have been measured for about 50,000 stars. So this is an example of one of the Kepler light curves. How does it work to measure the rotation period? Basically, let's pick a random star. The star is going to have features on the surface, either spots or faculae, for example. The star is going to rotate, and as we keep staring at the stars, the spots are going to come in and out of the line of sight. That is going to leave an imprint on the light curve. And from analysis of this light curve, we can derive the rotation period. This is now, if we go back to the CMD, what the rotation period looks like in the color scheme. And here there is a striking behavior that I hope you can see. All the rapid rotators are concentrated on the left, slow rotators are concentrated on the right. And this is due to a stellar structure, really. The stars on the left have relative envelopes, so they do not spin down as a function of time. They remain rotating rapidly. The stars on the right, they do spin down because they have convective envelopes. They're either fully convective or at least partially convective. But the point is that they spin down as a function of time because they have angular momentum losses via their magnetized winds. And this opens a really interesting possibility if we focus on the low mass stars. So this is showing now the stars with known rotation periods shown on the y-axis as a function of Gaia color or temperature on the x-axis. And here the color coding is the age of the targets. So here I'm only showing targets that have known ages because they belong to star clusters or associations, basically things that we can age date independently of rotation. So typically coming from the CMD. And this opens an interesting possibility because if you look at a given color, stars basically move vertically on this diagram. And if you can quantify the relation between rotation and age, we can use stellar rotation as a chronometer. So we can tell the age of stars by measuring their rotation periods. This is the so-called Skumanich law. Approximately, rotation period increases as the square root of the age. This is an approximation. It really depends on effective temperature, but it's good to keep it in mind. So this opens the possibility of doing gyrochronology, again, to age date stars based on their rotation periods, with the applications, of course, going to several fields, but just to highlight two, we can use this to age date exoplanetary systems, both the host of the planets and the planets themselves, and also for stellar population studies via galactic dynamics and galactic studies. So far so good. However, about 9-10 years ago, our clock broke. Let's put it this way. So this is showing for this is a small sample, okay? I mean, 15 stars maybe. But for stars that have really well measured ages coming from astroseismology, so completely independent from the rotation, independent from the CMD. So ages for stars that don't belong to clusters, so these are field stars, where we know the age from astroseismology, Vanceris and collaborators plotted as a function of the age the ratio of two numbers, the rotation period that they would have predicted given standard gyrochronology, divided by the rotation period that they actually observed. So if our theories of angular momentum evolution and they work well, we should be able to predict what we observe, no? So this number, this ratio is about 1 up to about the age of the sun, which is here in the black circle. But for older ages, we see that this ratio goes to values greater than 1. So the rotation periods that we observe are faster than what we would have predicted. So this phenomenon was called the weekend magnetic break-in. The transition is at about 25 days, and the physical origin for this is still unknown. One of the hypotheses for the weekend magnetic break-in is that really what is changing is that the star is being dominated, is that the dominant magnetic feature on the star is changing. And this amazing paper by Montet and collaborators quantified what the dominant magnetic feature is. So we have when stars are rapidly rotating, they are dominated by spots, and when they are slowly rotating, they are dominated by faculae. So remember, rapid rotation young, slow rotation old. So I've been wondering whether there is a connection here, because this transition also happens at around 25 days. If we look at a random star, we have our photosphere at a given temperature, and I've been trying to think what kind of signal we could use to see this transition in a different way. So spots are cooler than the surrounding photosphere, and faculae are hotter than the surrounding photosphere. So it would be really nice if we had chromatic information, and this is where Gaia comes in. Of course, the Kepler mission, the past band I am showing here in black, is basically white light, everything that we can collect. So it's super precise, but it has no color information. Gaia, on the other hand, as I'm showing here in the blue and red curves, does have chromatic information. So I'm just going to show you some preliminary plots of this pilot study to prove this anomalous rotation using the Gaia photometry. So here in the background, again, I'm showing the CMD, all the targets observed by Kepler. And in yellow, I'm showing the subset of those that have, well, first of all, that are bright, just to have a manageable number of targets, brighter than 13, that have measured rotation periods from Kepler, and that have been classified as having variability classified as solar-like. So this is about 400-ish stars. So for those targets, I have downloaded their Gaia light curves, and I am now going to show you those two examples. So as a function of time, either the apparent G-band magnitude in green, or the Gaia color plus some offset. The offset is just so I can plot them on the same figure, and that will be black. So some stars have the behavior shown like this. You know, we have some variability on the G-band magnitude, and really both light curves, the G-band and the color, BP minus RP color, are correlated. So they're kind of moving in unison. When the magnitude gets fainter, the color gets redder. On the other hand, and this is with some preliminary expectations we would expect for stars being dominated by spots. On the other hand, some stars show kind of the opposite behavior. Thank you. Where as the star gets fainter, the color gets bluer. And this would be more consistent with stars dominated by faculae. It's not so simple, but those are more or less some preliminary expectations. And now when we look at the rotation periods for these targets, we see that the target on the left has a rotation period of about 11 days, consistent with what we would expect for the rapidly rotating population dominated by spots. And the target on the right has a rotation period of about 45 days. So a slow rotator consistent with belonging to the population of stars being dominated by faculae. So these are some preliminary results, preliminary hints that maybe we can use this kind of information to disentangle what is going on in this process. So just to wrap up, I'll say that now in the Gaia era, we really have unprecedented databases for stellar variability and for classifications. Stellar rotation can be a fundamental tool for age dating stars. There is, however, a problem, which is the weaker magnetic braking. We're still trying to understand it even 10 years later. One hypothesis for this is that there is a transition from being spot-dominated to facula-dominated, and the Gaia multi-wavelength light curve may open a window to prove this phenomenon. So that's it. Thank you.
Thank you very much. It's super interesting to see that even with this Kepler cadence, and the length of the light curve, you can still use Gaia's, sparse cadence to complement. Simon?
Simon Hodgkin, Cambridge University. This is fascinating, really exciting. You have a binary sequence, single star sequence. For the binaries, are we seeing a rotation period, or are we seeing something else to do with the orbital modulation of the stars? So do you need to separate those out, or are you happy to lump them together?
Oh, that's a very good observation. Thank you for the question. I guess you mean here?
Yeah, and in your last plot as well, the solar light, you have obvious binary stars, right. Obvious single stars. Right. And I wonder with the binaries, maybe you're seeing something a little bit different than single stars, perhaps, or at least superposition of two signals.
Right. So just thank you for the question. So for some context, the thing is, when we look at the CMD and we have such exquisite precision on the CMD, as is the case for Gaia, we have our main sequence here, but of course, these targets up here correspond to targets where it's what we call photometric binaries. So they are so close together that Gaia sees them as one target, but we get the light of two stars. So really the position on where you are on this binary sequence will depend on the mass ratio of the system. But exactly as you said, for systems when they're going to be close enough, of course, the rotation rate may be affected by, say, tidal interactions or other phenomena like this. So one has to be careful. In this case, I have not removed the binaries just yet, but that for sure will be, it's usually taken into account when one does for example, the very detailed studies such as this. Here you take out all the binaries because you know that the rotation rate that you're measuring might be affected by something that is not just the evolution of a single star. But yeah, thank you.
But it's not only the rotation rate. So can you tell that it's not the orbital, what you see in photometry? I think that was right, the question as well.
So you mean that the period that you're measuring corresponds to the orbital period?
It would be a specific setting, right? Because there are some periods that you expect, right? And if the orbital period is just right, then I don't know how big the amplitude is, for example, for the rotation, but it can.
It's a good question. Yeah. I'll be careful with doing the one-to-one matching, but that's probably happening in many systems. Yes. Thank you.
So you remove binaries, right? You don't like binaries.
Well, it depends. I love binaries, but so far, no. So in this, yes, you are right that we're gonna lose 50 targets here. So let's call it 350 or 300. Yes.
Just to follow up, I suspect you will find that they're mostly short period binaries in systems, and they should stick out like a sore thumb.
Yes.
And then they should probably be synchronized, the rotation, the orbital periods, and you'll probably find they're spot dominated. But jury's out. Laurent has it.
Yes, and if you are on the sequence, there is a chance that they have similar mass, and so the color magnitude variation would make them to oscillate more vertically without much color changes.
Yeah, exactly.
That could be. I have another question. So have you compared, because obviously in the Gaia catalog, there is the catalog of Di Stefano, which provides periods. And obviously, we are not sure, because of the sparse sampling, that they are so good, or if there is an alias. Have you compared the period of Kepler with Gaia?
Yes, so this is a very good question. Thank you. So exactly. So how good can Gaia recover rotation periods? Because if we look at the x-axis in this diagram, this goes from 10 days to 35 days. So with the Gaia sampling, it can be hard to do this. I did this comparison a couple of years ago when the R3 came out. I believe it worked well for the most part, but again, Gaia is limited to the short periods. So the distribution fell like a cliff, basically, after 5 or 10 days. There were not very many Gaia rotation periods, but I think where there are, the overlap was good with Kepler. But I can double check and we can talk about it during the coffee break. Yeah.
Okay. I think we hit the time, so thank you again, Diego.
Yep.
And the last speaker of this morning session of today will be Milena Ratajczak on ellipsoidal binaries. So the stage is yours.
Thank you very much. Hello, everyone. I'm really thank you for introducing me. Thank you for giving me an opportunity to talk in the Gaia session. I'm going to tell you about ellipsoidal binaries, which are actually variable stars. They are non-eclipsing closed binary systems, where at least one of the stars is not spherical, but it's ellipsoidal due to tidal interaction. So what we can see with the light curve and photometric changes here are mostly related to this ellipsoidal modulation induced by tidal interaction, but sometimes we can also see some effects of reflection of each star's light from the surface of the other, and also some type of more sophisticated relativistic Doppler beaming, but I will skip this too, and I will focus on this ellipsoidal modulation induced by tidal interaction. It's related to the fact which side of the star we see, because we observe the system from different angles depending on the orbital phase. So depending on the phase how we see the star and which part of the star we see or we see, then it's either brighter or a bit dimmer because of the surface that we actually look at, if it's more ellipsoidal or more spherical. So binaries. By DOMA, compact objects, I mean black holes, neutron stars that are in that do not emit any X-rays. So they're like sleepy and quiet, but actually we can search for them in a massive surveys that we have nowadays. So obviously the most natural way to find this kind of system is search for large amplitude radio velocity modulation. But for that, we need a lot of high resolution spectroscopic time, which is expensive. And since many of those targets are really faint, it's not easy to get big telescopes to have radial velocity tracking all those systems. Obviously, we can also use spectrometry, and we've heard about extreme perception in Gaia data. So we know that there are several black holes already found with astrometry. This kind of dormant compact objects in binaries by using astrometry from Gaia and also some additional data. But since we have quite a lot of large surveys, photometric surveys, we can use them to actually search for ellipsoidal modulation induced by tidal interaction. So to look at ellipsoidal binaries, and we can take a look at the ground-based data like or space observatories like Gaia or TESS, since they have quite a lot of also photometric data. Since I'm the first person talking about this conference, and there are going to be a few talks to this slide on introducing the optical gravitational lens. It's an experiment, a very long sky photometric survey that is carried out for more than 30 years, but most of the time with a one called 1.3 meters located in China. And the main power of the is there are two, like the strongest point of OGLE. One is the fact that it is a really long term, it's 30 years of data, and another is actually pretty big view. So you can see at the plot here, it's a snapshot the mosaic CCD camera of OGLE 4 with a field of view of 1.4 degrees. You can see actually 6 million stars at that one picture. So we monitor the southern sky since the telescope is in Chile, focusing mostly on those fields of our galaxy, namely galactic bulge and galactic disk. But we also look on the neighbor galaxies, so Magellanic Clouds that are located here. So this are actually the fruits of observations for the OGLE projects. OGLE, as the name says, it was mostly designed to work on gravitational microlensing, but it's a science factory, and actually the data from OGLE also as a learning also for the Gaia mission variable stars, and in between those data we also have also ellipsoidal numbers. So those ellipsoidal systems in OGLE, they may look like the one light curves that you can see on the left-hand side. So we have more than 26,000 of them that are already that are found in the OGLE data, and the range of the periods and the brightness variation is shown on the downside of this slide. So you see we have a short period. So have some periods coming up to almost 2 years with the changes of amplitude going to all the way to 1.2 magnitude in an E-band that OGLE is observing in the most. So what we can do with this data? So we can work on the mass ratio. So what we can do, we can take photometric amplitude because we see the changes in the light curve. We see the sinusoidal shape, and we can we know what's the amplitude of those changes. And if we know the mass and the radius of a visible star, and we assume that the secondary star in the system is not visible because we see only changes, ellipsoidal changes from one star, and we assume that inclination of the system is 90 degrees, we can estimate something that we call the minimum mass ratio, which is invisible object divided by visible object by mass of the visible objects, and that's the minimum mass ratio of that. But for that, we need the information about mass and radius of the visible star, which is not always given. It's actually pretty challenging sometimes to get it because we need spectroscopy and we need some additional data. So that's why there's something called modified minimum mass ratio that was introduced by Gomer et al. In 2021 that actually depends on a photometric amplitude only. So we don't really need information about mass and radius of a visible star. We just need to assume that the primary star fills the Roche lobe and assume the inclination is 90 degrees. And we have only from photometric amplitudes, only from the light curve, we can actually calculate this modified minimum mass ratio, which is almost smaller than minimal mass ratio, which is than actual mass ratio. So if we have, for example, modified minimum mass ratio larger than 1, that means the secondary component is more massive than the visible component. So we may assume that it could be a promising candidate for some compact objects because it's a massive object, more massive than the visible one that is not visible. So it could be some kind of like black hole or neutron star. But it's not so easy because it turned out that in this work I'm showing here, 8,000 candidates from the OGLE was analyzed, and we found 14 large photometric modulation stars with energy distribution of single stars. And also, so we have like big photometric changes. So this modified minimum mass ratio is larger than, let's say, 1, and there's SED of single star. And the third information that was taken into account was actually the error in radial velocity in Gaia DR3. And Gaia DR3 didn't give us individual radial velocity. It gave us medium or mean radial velocity together with error. But you can actually imagine that if you have a star that changes radial velocity a lot because it has a big amplitude changes in radial velocity, it may actually happen that the error is big because of the orbital phases and the measurements that you find. So from that you can get some very like the estimation of radial velocity semi-amplitude, and from that you can actually calculate the minimum mass of a secondary component. And you see that the most promising candidate is I'm showing here. It's 120 kilometers per second amplitude, which goes to 0.8 solar mass. It's obviously not the mass of a black hole and not the mass of a neutron star even. It could be a white dwarf, but it is a minimum mass. So it could actually happen that this object is actually 1.3 solar mass, already could be a neutron star. But the challenge here is actually turns out that all of the system, all of the 14 systems, we can model with the light curves of contact binaries. So here you can see the light curve of one of those systems, and the blue that is visible here, you can actually fit the model of a contact binary. Since contact binaries, there is much more contact binaries in a universe and compact objects with binary systems, we may assume that actually most of those stars are contact binaries. So let's go to Gaia. So there is 262 dates taken into account. They are too faint for Gaia radial velocity measurement. The light curves you can see here. So there's a whole variety of light curves that could actually host this compact objects. And for this system, the follow-up was taken, and then actually that turned out that 14 were chosen, and they were chosen based on the brightness. So it's not the best candidates in terms of this minimum mass ratio, but the brightest. But it turned out that actually they all have secondary components that are too low in mass to be compact objects, and they also can be modeled with the light curves that are related to contact binaries. So what we started to think was if there is any way to actually look at those systems without additional radial velocity data that are expensive, as we saw. And here we actually look at the three scenario main sequence black hole binaries and contact binaries, and we check with a Phoebe software the color changes, and on the red color is the R light curve, the green color is V light curve, and the black color is actually the changes in color. But it turns out that for all of those three scenarios, it is actually the very similar in color. Cannot use that for distinguish which scenario of the system it's actually following. So what we need is the spectroscopic data. This is an ongoing follow-up program that we have on high-resolution spectrographs. And then the very last I would like to mention is that there are very special class of ellipsoidal variables that are called eccentric ellipsoidal variables. The eccentric orbits. These are called stars. And what's interesting here is that like a very eccentric orbits at periastron that come close to each other, and they are also have the interaction, and they're changing, and the light looks like this in this shapes, where the radial velocity look like this. So we started to look at this objects and the early data the thousands of this kind of systems. And I would like to show the one last of the things. It's the amplitude period diagram of the EEVs found in OGU, and there are two extremes. One of the extremes is extreme in amplitude, and another extreme is actually the extreme in period, going all the way to 3 years. And the first extreme, it actually turned out to be a very interesting case. Wind-wind collision, and that was also studied in terms of tidally excited oscillation. I will spare the details. We had some following up a campaign, and the last one is actually the one that was a long period of 3 years. We haven't found the secondary in the radial velocities here, but we actually have some models of this data, and it seems that is also a very interesting case of stellar revolution of binary system that was and with a period more than 5,000 days, and it's right now it's a red giant and main sequence star, and so you can read here. Thank you very much.
Thank you. So now we have time for questions. So Simon, Paulina, you should be next to Simon, I think.
Only if no one else has a question. Simon Hodgkin, Cambridge University. Can you use the period in any way to help weed out the contact binaries from, presumably there are some kind of contact binaries that just won't fit in a short period, or some configurations are less probable. So I wonder if there's any way to use the period information.
Yeah, so obviously there's the radius of this, and yes, this is very helpful. So like regimes where we know that one of the stars can actually fill the rush load, or two of the stars can fill the rush flow. So too close to overcome and so on. So this is helpful information. Although in that case, we always take into account this period regime in terms of contact binaries, that they could be the contact binaries.
Yes, so thank you for your presentation. I have what you said in your presentation is that you cannot distinguish from color ellipsoidal and contact binaries, and you need radial velocity, right?
Yes.
Okay, so
yeah, so because that was the way that we wanted to actually approach to those DR3 candidates that turned out that many of them could be contact binaries, and we also started to think what to do without radial velocity. Is there any way that we can, for example, design a BH-TOM campaign to look at the different colors, or to use Gaia colors if there are enough to see? But it seems as it's shown here, that the peak-to-peak variability between these two scenarios is very, it's almost the same. It's 0.01 magnitude. So they're very similar in colors, in changes of colors. So that is not helpful in that case.
Now with the D4, there will be the radial velocities. So that means you will be able to distinguish them.
Yeah, for the brightest targets, unfortunately, majority of the targets that were in the list of Gommel and Mazur and so on, they are too faint for having radial velocities from Gaia. But there is some of them that goes to that. And for those brightest targets, we already did this exercise with this radial velocity semi-amplitude that was estimated based on an error of radial velocity. So not on the obviously individual is perfect, right? For the bright targets, but yeah.
Distribute.
Yeah, I collaborate with Svi Mazek on that. So.
Okay. Any more questions? If not, then let's thank Milena again.
Thank you very much, and enjoy your lunch, right?
And all the speakers of the morning session. So now lunch is ready. I just would like to remind the speakers from the afternoon session, please, first of all, upload your talk because we are still missing some. And if that was not in a PDF format, there are two that were sent in the format that will probably not work well. So please, all the speakers, check with the log table the presentation before we will start the session. So the lunch is served outside. We will meet again for the session at 2 o'clock.
Wyślę, tylko widzisz, laptop jest zajęty. Poczekaj, tylko wyłączę tego streamu. No i bardzo dobrze, ale co też mogę powiedzieć w moich slajdach, że teraz mamy Warszawę i będzie szybciej wszystko, nie będzie zastojów w kolejce. Rób zdjęć dużo, Gabi. Rób zdjęcia. Ale jesteśmy na YouTubie ciągle, wiecie o tym. Że chyba nie mogę tego zatrzymać. Znaczy, boję się, że nie wystartuje drugi raz. Line the sound drops out when the speaker talks too close. Nie. Bo ona tylko serwuje do 11.
Whenever you have time to raise Diego and the room co-host of the Zoom so that we can mute people from there. Because right now.
Sala is already.
Okay, yeah.
Co-host.
Then make Diego as well. Because if I mute people from the Sala computer, then everybody sees, so it's distracting.
Okay, that's
So
what
if
I was
Diego-
wondering.
Yeah, if Diego has
Okay,
power.
Diego
then he
has
can
power
remove-
now.
Thank you.
I don't know much about astronomy, but I understood some of these.
Thanks.
We're talking.
Good, that's good to hear.
So this is over for you when it comes to speeches?
Yes.
So now you can just be a super green.
Yeah, I am now, yeah, I'm just running around. Mhm.
So, you know, I didn't mention something nothing to do today, so I went out.
And then
She
you-
said they serving coffee from,
Ah.
and I was falling asleep.
Yeah, I can actually give you a recommendation. If you just meet the park that way, you are gonna have like a local bar with coffee for like euro 20, and it's gonna be good coffee because this is the one.
Okay, good idea.
Have a quick sip.
Yeah.
And come back, right?
The
Especially
thing-
when your boss is not.
Yeah. But no, I think last time we had the same problem. We also wanted coffee after lunch. This time we asked for it specifically, but last time we didn't, and they didn't give us. So I think they're very much working in blocks.
Yeah,
so-
but they're there all the time. Like I got a coffee when I first arrived because she didn't get someone older coffee. Yeah, she goes away like this.
Yeah.
Because I took for myself on the
Yes, exactly.
No, someone must have thought some of your organizers. Because I found walking because I took the coffee and just saw it coffee in the morning, and it's just right. Yeah, so perhaps he told them.
Okay, I haven't talked to them.
Talks about.
Yeah,
Spanish, because I was like. I really think you should, because you should. That's okay.
But no, I think that I feel that.
Sprawa teraz, 30? Wypijesz jeszcze jedną z mlekiem?
Flat white.
Wet white, no sugar. No sugar.
Kawa, woda, mleko. Dobra, kawa, mleko. I to nazywają kawę con leche. Nie, ale muszę zacząć od kawy rzeczywiście. Przed lunchem. Spałem dobrze, a ty słyszałem, że nie spałeś. Teraz musisz wydać. Rób zdjęcia. Są dziwne. No, realnie. Tak, on mnie wymienił. Dobra, teraz brakuje mi, muszę ścignąć pana Stasa. From nie dał mi wersji złe. Nie, nic filmem.
Jeśli nas zaraz nagrywają, to potem wiedzę przyniosę kawę, ale może wystarczy.
Poczekaj, muszę coś puścić. Możemy... Przyjdę. Dobra, przyjdę.
Looks like important stuff, huh? Exactly.
I think this is session 2, Monday, and yeah. So that's me, that's my. Yes. Oh, this is not looking good because all the fonts are installed. You know what?
But can you put animations on the piece?
No, that's.
Are they sure though? Like people keep saying no, but I'm sure I've done it. But anyway.
Yeah. So I said the other option should be that I could connect my own laptop and just have it from my own laptop. So
Yeah, I would say.
what do you have? So would
No,
I
no.
be sharing by Zoom?
Yeah, so you would connect by Zoom, just like an online.
Okay.
Connect by Zoom. Basically, we have the Zoom on that one, the corner. And this one is connected to the Zoom. So
Okay.
we're actually not projecting to this one, we're projecting now. Yes. We can try it now. I just uploaded mine by the way. Yes, yeah, because so we had a yes. Ah, yes, yes, yes. Is there anyone? Yeah. But I will not be surprised. Yeah.
I just uploaded mine and renamed it. Can we open it?
No, there's no PowerPoint.
Oh, there's no. Okay, then I need to go online. How did
No-
you?
no PowerPoint,
How did you
yes.
do it with sharing? You did also connect or?
Yeah.
Neither.
But if there's no PowerPoint, it's not PowerPoint, yes. You can save that in PDF. That's no possibility.
Yeah, that's no question. We should put it down there or something.
For what? For my presentation.
Just put it on that table to him and then.
These connected. Yeah. How do you present it as soon as well? No.
Just.
But do you have animations?
Yeah, one animation. The key takeaway message is animation.
Also, I think.
It doesn't have PowerPoint. I thought it had.
But they can have animations. Really? Yeah, like to do animations. The other thing is we just start telling people to connect this.
Yeah.
Should we do that? I mean, this problem here is no PowerPoint, no. Not Microsoft,
Yeah, I was looking for you to talk to Ignacio about how to close. Porque es un-
¿Verdad? Dame 3 minutos. Padre. So if you, yeah, so that's your PowerPoint. It opens in Keynote.
Okay.
But you should double check if it works.
Yeah, that's what
okay, right?
what I want to check. Yeah.
So there, there's some
No, there's
things
actually
missing. Just
Where
go
do I
through
where
it.
do I full screen play?
There might be some changes in fonts, so it's. Works perfectly. Yeah, you can do animations like that. I think they have improved recently because previously my experience was that PowerPoint open to the Keynote had many issues. Now it's better.
Just want to check one thing. One more thing, because the takeaway messages are as an animation.
Works. So that's what we observed. Wow.
As it goes up, that's what we observe.
Cool.
I like the animation. It's really showing what you mean. Great.
Okay, thank you.
So keep it open there. I need to chase one more.
Yes, put the when everything's settled, either the program or this big I will make a slide in the Google Sheet, which we can use for like 16.
But that can be run from there.
But whatever, if you have it like this.
Yeah, because occasionally, during the breaks, I need the laptop to set up the presentations and so on.
Yeah.
So it's better to do it
Don't
from
talk
the
about
other.
them. Don't talk
Yeah.
about them. Yeah, but I'd like to have a slide, because then when you have pictures and you have.
Sure.
Yeah. Great.
Great. Już sprawdzamy.
Tak, jasne. Quick other question. When people are using their notebook with Zoom, what should we do with your notebook? Put it on your desk or put it on here?
Don't let them. Don't let them use their own laptop. Eustace, you want to use your own laptop?
What?
You want to use your laptop?
No, maybe not, but but here is no PowerPoint, yes, or? No.
No PowerPoint. I need a PDF from it. Convert it to PDF. Because you have a very short period of time. 5 minutes, 3 minutes.
Yeah, but I have one small animation and
Animation.
do it. Or maybe you just don't like separate file. I think
Okay.
also I think it's like that. Presentation and small animation. It can work for me.
What is the format of your animation? Because I cannot open this.
Yeah,
Unless
we try this, don't open. Yes.
yeah, I'll try. I'll give it a try.
I think it can.
I'll see. I'll install LibreOffice and we'll open it in LibreOffice. You're last in the session, so yeah. Trying to open LibreOffice. Welcome to LibreOffice. Oh, but you need 2 slides. Come on, you have 3 minutes. Yeah,
Skip.
Yeah, but it's better to remove some slides so that then. Okay, let me try play it. Slideshow. So this animation, maybe we can. No. Doesn't work. Okay. Media play device. No. Doesn't work. Weird. Can you send me when you upload the animation itself?
Yes. Yes.
Okay.
At the end, I can after that.
Yes, and remove some slides. So I have LibreOffice now.
And does it work?
Partially. Because it does work, but except the animation. Somehow. You know why?
How many cars we have? Because there's still more people sign up for the tour than we have spaces.
Yeah, we can ask. We can ask people.
Simon has a car, no?
I don't have a car.
I have a car. If people need a lift, I can do it. No, I'm leaving my car. My car's gonna stay here all week. So
Yeah, but we're talking about the tour.
Wednesday too.
I'm not.
Wednesday.
No, I'm busy on Wednesday. So
Okay.
we're not-
I think we need a list of, and ask people to double check and, to know how many we have, if everyone is going. And who we need to put on cars.
We need at least 2 cars, I think.
We can do it and ask Nigel or
Version K keynote was next week. Yeah, it'll be enough. We'll just go to the. Ah, you're.
Yeah, it's already same.
Oh.
It's fine. Can you go into the session? I asked the movie.
No, we have this from our.
Just
There is still people.
We might want to make a list. Yeah.
Danas, you like the movie?
Famous Sergei's movie. She's done this.
That's this one. should be fine. Which I probably won't. I might show you. The standard size.
Pretty cool, yes.
I was happy Anna showed it. That's just like thanks. I missed that.
Well, give you credit. So.
Yeah.
Okay, so I can delete the other ones.
You can delete everything else in my.
Okay. Delete.
These two. Go.
Oh yeah, this yours.
Okay.
So there are also formats.
Yeah.
Okay. Thank you.
Milena jest.
Milena tutaj jest.
Na
Zajawkowała. Czyli mogę skasować jedynkę, tak?
Tak.
No właśnie o to chodzi, nie? Że ono się...
No to zobacz PDF. Mamy tu PDF. A, no to to się
sprawdź. Bo czasami właśnie mogą się różne rzeczy przesuwać. No?
No, to jest mała różnica między wersją 1 a 2.
Przypomniałeś sobie, a po cholerę ja tu przyjechałem. Dobra. Ale dzisiaj nie jest 9 septembra.
O,
muszę ci poprawić slajdy, no. Dobra, to mamy.
Dzień.
So far, so good.
W sensie na końcu konferencji, czy na końcu dnia? Ja bym chciała
No tak, też.
ale to też nie musi być teraz, musiałam tutaj była.
To już tak. Ale wiesz co, dużo się dzieje z chłopakami, że po prostu jak ludzie wrócili na hotel, nie podniosą nas łapy, jeżeli to znajdują, tylko znają na to nie jest.
Nie, ale to są, nie, dosłownie.
Nie, no bo takie momenty,
Ale
Simon mówi, że na inteligencji teraz on czuje przyjeżdża, to ludzie na wschodzie pokazać,
Znaczy wiesz, ja mam ale nie, no też nie było tak, to prawda. Ale ja wiem, że to, ale ja mam, ja na przykład no, super. W sensie, ale nie, no super, ja mam bardzo
no to dobrze. Ale mimo wszystko przy tym głównie rozwiązać zakończyć to podnoszenie.
Ja też bardzo powiedziałam, bo u nas
ale to jest będzie struktury.
no właśnie, no okej. Ratuje Radek tak, nie? Oni
No właśnie.
To jest
I
ciekawe.
dlatego mówię, że tutaj pytam. A ci z góry nie wydają odpowiedzi. Bo się boją, jeszcze to są głupie pytanie, a jak profesorowie się boją, to już tym bardziej. No to chodź. Mówisz, że też ma. Właśnie wiesz co,
Ale faktycznie. Ja podchodzę. Czekaj, czy zatrudnię. Ale nie. W sensie, ja mówię jeździć, nie no, wiesz, no ja...
Raz kiedyś przysłał. Nawet nie jest ważne. Jeżeli wystarczy.
Aha,
że jeden recenzji bardzo zaproponujący, to był bardzo miły.
Nie, no ja wiesz co.
Ale mam inny pomysł.
Ale tak na...
No,
co ma? No ale no ale jak teraz ja wykonałam na no wiesz, ale jak ja mam wiadomo, że
co jest?
Jeszcze to powiem sobie, że to jest się. Znaczy, no okej, to nie kupię 4 panty. Ale dobra, to może to... I tak wiesz,
recenzji to zawsze są.
Byli takimi znaczkami, nie? Poczekaj.
Ja musimy zastanowić się, komu dało te
A, to super. Ja myślałam,
Teraz składam, tylko że one są słowa.
Jak ja dziękuję, bo przyjechałem tu po drodze idziemy na jakiś pasek, tak, będzie jakaś plata.
Nie tylko wy byliście
ale bardzo jest. Ale Andromeda? No nie, ale to jest w ogóle ten test.
Czego nazywa się?
Nie, nie, nie.
Palmira.
No.
Widziałem pani update. Kiedy mam czas?
Od sponsora. O, wszystkiego prawie. Macie jakieś taką. No bo dzisiaj jest czwartek na wakacje. Na paralizie. Tak, Nie na to
My sobie pogadamy.
Właśnie po to jestem na tym, że co? A ludzie nie? Tak, ja w tym roku moim kalendarzem. I się całkiem odrucha.
Słyszał tu? Słyszał?
Então, you get up, how we get up.
Lei sì che siamo qui.
A, jeszcze mamy kwadransie. Dobra, idę kawę.
Naprawdę?
I'm going to be switching presentations as well, yes. Right. One more minute. Okay, couple of seconds left until the end of the lunch break. But I'd like to invite the speaker
Okay, we can start now. Okay, so welcome after the lunch break. Now I'm changing my hat to be a chair, not of the conference, but chair of the session. And the next speaker, we continue on the topic of binaries, but we now will hear about the OGLE project by Mateusz Mróz. And where is Mateusz? Ah, there you are. Use my laser. Yeah. It's really fast.
Hello, everyone. I am Mateusz Mróz from Warsaw Observatory. I am currently finishing the PhD over there, and I will talk about the hunt for exoplanets in the direction of galactic bulge with OGLE project. First of all, as you probably most of you know, OGLE initiated two important methods of detecting exoplanets in photometric data. First of which is transiting technique, and the second is, of course, microlensing technique. I will start with transit method. First transit detection of a planetary companion was done in 2001 in OGLE data. It was the first time when this method was used to actually detect unknown planet. And it's opened the way for big space mission like Kepler or current ongoing TESS. As you can see, I don't know, it's me or somebody else is doing it. Okay. As you can see, detecting exoplanets in photometric data is pretty challenging. The signal of the transit compared to the scale of the whole light curves is pretty weak. And it makes even more challenging when you consider the actual density of the galactic bulge fields. But since this discovery, already 20 years, more than 20 years passed, and OGLE data still working, OGLE project still working, still observe the stars, and still gather the valuable data. And this where my work starts. I initiated my PhD project with search for next generation, let's say, candidates for exoplanets. I use for fields, the most dense fields of OGLE in the direction of galactic bulge, and you can actually see the combine for actual images from our camera. Just to narrow down the number of as Milena previously told you, in one of those fields, there can be even 2 million of the stars. But to narrow down the search, I selected only the brightest objects and only those that are on the main sequence. And you can see the cut over here. But still, it was this cut resulted in almost 250,000 of the light curves, which I personally check every one of those, and I end up with after many steps and many modeling, many validation process, I end up with 99 planetary candidates, highly probable planetary candidates. You can see the animation of many of the zoom in live curves on the transit signal. As you can see, the OGLE provide a lot of data points, photometric data points, which enable those detections. Most of those candidates are hot Jupiters. You can see on the plot the period or effective temperature versus the predicted size of the planetary companion. As you probably know, most of those from the transiting light curve, you can only establish the ratio of the sizes of the companion and the host. And this is actually what great input from Gaia is, because it's really can help maybe doesn't have the high impact on photometric measurements of the time series of the transits, but can really help with parameterizing and making some assumptions about the host of the planet, and therefore constraining the properties of planet. What was the case for this catalog? There are, as I said, there are all hot Neptunes, with one exemption, Ogle TR 1003, which I assume from the model, I can assume that it's one of the few planetary candidates from the hot Neptunian desert. So I will make a short break between moving to the microlensing method and to ask the question, why even bother to look for planets in the galactic bulge? Because as I said, the field is super dense. The probability of false positives is really high. The photometric extraction is really difficult. And as you know, we have other surveys, other missions that are dedicated to detecting exoplanets through transits, for example. But those surveys are limited. You can see over here the detection from great mission that bring lots of exoplanets, Kepler mission. Even when you consider the detection from TESS as well, which was whole sky survey, or all transiting exoplanets, you can see that only limited part of our Milky Way we prove with those surveys. And this is a problem, because when we want to know how the exoplanets are created or evolve, we need to put it somehow in like environment. And when we probing only like really limited environment, then it's also really difficult to put some constraints on our models of planetary systems. And actually, looking to the direction of galactic bulge, we can kind of bridge the gap, at least in a sense of galactic-centric distances. And this sample was, if those planets will be confirmed with radial velocities, they will give the insight into the distribution of the planet in the direction of the galactic center. And those results will be complementary to the results from microlensing surveys marked here in green. If you want to look through this catalog, there is a QR code over here. And you can also find other catalogs of variable stars from Ogle. As you know, they are a gold standard of catalogs of any variable stars. I will skip that, and I will move to the microlensing, because this is the topic that I'm currently working on. From what I see in the room, most of you probably heard at least once about microlensing. Microlensing happened when we have background stars, source of the light, this light is bent by the object on our line of sight, bent, and we see the amplification. We call this amplification a microlensing event. You can see the example of the light curve over here. And of course, this object can also have a planet. And actually, the microlensing method is unique in a sense of detecting exoplanets, because it can detect planets that are much farther, or even unbound planets. And actually, those microlensing events with the planets can result in really extremely nice results. For example, about the statistic of a white orbit planet. By white, I mean 5 to 15 astronomical units orbits. You can see the two peaks in the light course of the events. There you can kind of imagine that the distance between those two peaks are related to the size of the orbit. And based on such kind of event, my supervisor recently published really nice results that almost every microlensing star have the ice planet companion. Ice mean like Neptune size on a large orbital distance. Other important result from microlensing is search for free floating planets. We can also do that with microlensing, and there are results saying that there is no large population of Jupiter-sized free floating planets, meaning that probably most of the mass is ejected from the planetary system through smaller mass objects. And this is actually a part where I say about my work. One of the things I'm specializing, trying to specialize myself is modeling extraordinary planetary microlensing events. This is one of the examples when you see the planetary anomaly really small. And this whole analysis resulted in pretty extraordinary system, meaning that it's high mass planet are really low mass host. By low mass, meaning somewhere from the border of the brown dwarf. The other event that I'm analyzing is event that showing a lot of influence of the orbital motion of the solar system. And since we are here on the Beachstone Gaia Alerts conference, actually, as mentioned before, microlensing event can be degenerate. There are many different interpretations of the event, and undoubtedly the follow-ups or collection of many observations even from the small telescope, but in multi-bands can help to solve the degeneracy and told us what kind of astrophysical object we are seeing. And that's it.
And thank you, Mateusz. Are there questions to Mateusz? Milena.
Milena Ratajczak, Warsaw Observatory. Thank you, Mateusz. In the graph that you showed in the direction of the galaxy center and so on, and you probed a different type of planets, there was one planet that is actually in a direction that is a microlensing planet, and it's opposite to the direction of a galactic center. Is it a special case? Because it's not easy, I guess, to find planet in the other direction that the galactic. Yeah, even two.
There are a few cases, and it's not easy, meaning that it's less probable, and Ogle doesn't observe in other direction, but there are cases of events. I don't know actually if those events are from Assassin or other surveys that probe the whole sky, but there are microlensing events in not only in the direction of galactic bulge.
I have a quick question before Simon. So what would be your advice for small telescopes willing to contribute to this science? Of course, the bulge, it's probably challenging for small telescopes even more, but there are some other fields like outside of the bulge. What would be the best data set you can imagine you can do your science?
So any information about the source of the light in microlensing event, meaning that you don't have to specifically observe the whole event, but the multi-band observation of the source, characterizing it, put some constraint on microlensing event, and it actually can be really helpful. It's pretty difficult to, and it's a bit, I would say, like new field in microlensing, to actually use any other information outside of like typical microlensing survey or follow-up. And I would say that would be multi-band observation of the hosts that can be performed.
This you have from Gaia, for example, right? Because the source is there.
Yes.
But I mean, for the actual event, when it happens and there is this anomaly coming.
Yeah. So if you look closely on the BH-TOM screen that I show you, actually you can see the last Gaia release time series that are only cut on the beginning of the event. So actually, I don't know if in this case how Gaia will be helpful, but definitely, because if we have multi-band observation during the event, we can establish the light of in many colors, fluxes of many colors from the source and from the lens, with some assumptions, and therefore when we can probably in good cases we can assume the whole, like treat the source of the light in microlensing event as a fully determined astronomical object.
Okay, thank you. I think we have to move on. Simon has to wait for his question. So let's thank Mateusz again. And now give the floor to Paul Beck. This is your right. Okay. I want to use this. I want to use it. Okay. Okay. Floor is yours.
Thank you. Good afternoon again. Now it's my pleasure to present work that I've done here at the ISC. I'm a mid-senior researcher here at the ISC, working with Kepler and TESS. And I would like to tell you a few tales about how to combine them. So first, we are starting with astroseismology. Astroseismology has seen a major boost with the advent of Kepler and TESS. And we have a couple of 10,000 stars that do oscillate in solar oscillations. And they are very neat because we just need to measure what the frequency is and a couple of parameters, and we can determine mass and radius. And I spare you all the confusing details and spoil you with a press release picture. Red giants also have a very specific characteristic that the oscillations reach the core. And therefore, we can measure if the core is degenerate or convective, and we can separate between different stages on the red giant branch. And this is what we like to use for large sample studies. Now, astroseismology needs to be calibrated, and the best calibration devices are stars in binary. So what do we need? We need solar oscillators. There we have about 40,000, and we need systems with known inclinations. And then we need a double-lined binary to calculate the dynamical mass. Until now, this was only true for eclipsing binaries, and we had about 20. Now with Gaia, we can search for new eclipsing binaries, but we hardly find them because the red giants are too long to have eclipses. But we can also use the astrometric binary to calibrate them. But there are only a few thousand. Using Gaia, we have found the first eclipsing binary showing oscillations in the southern field, which conveniently is located in the Plato field. So here we have one more target to the 20. Now, what do we do with all the rest? The eclipsing binaries are just the tip of the iceberg, but we have thousands of non-eclipsing binaries at any other inclination, in particular reported by Gaia. What do we do with them? And well, we can search for binary populations. I show you a Hertzsprung-Russell diagram from the APOCAST-3 catalog that is providing homogeneous cosmology and characterization of 10,000 stars. If we from the bottom of the red giant branch to the tip, to halfway the tip, and into the red clump of helium core burning. Now, how does the binary population change? And here we can use Gaia to determine the binary rate. What I show you on the left is the two-body orbit solution, and on the right, the linear and the acceleration solution, and Ruven. Basically, what we see is that from the bottom to the tip, it seems that they are diluting. And because we can separate between helium core and hydrogen shell burning stars, and we have the mass, we can separate them in different evolutionary channels. And we can show that, for example, if we have a degenerate evolution of the core, we are dropping from 30 to 40% on the main sequence to 10 or even 5% on the red giant branch. So we can trace the dilution and attrition of the binary rate as stars are evolving. And then this one is staying constant as stars reach the helium core burning phase. Now, with Gaia, we have the two-body orbit solution, and we can now check for the large sample for different properties. And when we use the seismic information on the evolutionary state, we can see how the orbital parameters are co-evolving with the binary, with the stellar evolution. Let's start by the main sequence stars, shown in yellow. They have they show the birth distribution of eccentricity versus period. And on the right panel, you see orbital period versus mass. We have a consistent distribution. Now let's allow the star to evolve away from the main sequence. And we actually see that we already are not covering the very short periodic periods below 20 days, because the star is evolving. And suddenly, the orbit of a 10-day binary is too small to host the growing giant. And this will continue. At the tip of a giant branch, the star will be about 200 times the solar radii, and it requires 500 to 1,000 days to allow for both stars to stay in the orbit without interaction. So we expect that actually the cutoff period is shifting. And this is what we get when we look at binaries with helium core burning stars. They are starting between 500 days to 1,000 days. And the cutoff here is the baseline of Gaia. So we can expect them to be even extended. But this is for the degenerate helium core burning ignition. If we go into the non-degenerate helium core burning ignition above roughly 2 solar masses, we get a wider range. And this is because stars can ignite helium at much lower orbits. They do not need to get to the tip of the giant branch, but ignite at around 80 solar radii. And that's why we can find helium core burning stars on much shorter periods. So basically, this is a shoreline and showing us the imprint of stellar evolution. But we find a couple of stars below that shoreline, and those are typically rapidly rotating stars, probably merger products. And using seismology, we can make distributions of the mass. What I show you is a distribution of the masses of the full Kepler sample of EPOCAST. We see basically a very homogeneous distribution between the hydrogen shell in orange and the helium core burning on the right-hand side of this violin plot. If we are looking at the binary sample, we see that on the red giant branch, the binary masses are very similar to the full sample, but we find the helium core burning sample significantly shifted to higher masses. And that's a selection bias, but that small period binaries talking lower than 1,000 days are undergoing a common envelope phase and will be destroyed. If we are looking at the rapidly rotating stars, what we are seeing is that they are significantly below the average mass, which we consider as the merging product. So they had undergone interaction and lost significant amount of the outer envelope. And this can actually be considered as the big picture, that when we are looking at stellar, that we see the co-evolution of the binary orbit as the star is evolving on the red giant branch, as the star is growing bigger, we have circularization effects, but also the effects of merging on common envelope that are selectively destroying shorter orbit binaries. And with this, I think I made the chair happy, and thank you for your attention.
I'm not so sure if that makes me happy, but let's see. Are there questions to Paul? Yara. You have the mic.
So with these few stars that were in the forbidden range, you said mergers, but these would be mergers of former triples, right?
Well, most of them actually they're still binaries. They could be triples. Probably they somehow survived the common envelope phase or have undergone significant mass loss.
But then they're not mergers, no?
Well, they have undergone common envelope, and some of them are mergers, some of them are still binaries. We have 70% binaries in that sample.
Yeah, but
which is much higher than the main sequence.
Yes, I'm just thinking that what you were showing were all binaries, no?
The rapidly wrote, those that are in binaries, they have significantly lower
So if
masses.
these are post mergers, they were triples.
Could be.
Okay. Any more questions? We have plenty of time. Laurent.
So I'm not sure I understood everything there, but so you have a reduction of the fraction of the binary system, and so which range of stars mass range do you speak? And is it by the same process that suddenly you have that you don't have much or no RRL arrays in binary systems?
We're not talking about RLI arrays.
No, is the type of system, there is this mystery why you don't have binaries. So if you have a mechanism that is eliminating the binaries, would it work the same through the same mechanism?
Well, the mechanism is that the red giant, the more massive component, is growing. And if the binary is not wide enough, it will fill the Roche lobe, and we have this mass loss. Or we have going to common envelope phase, and then it might leave the red giant phase because we are losing the star is losing too much mass. So those are all solar-like oscillators in the red giant phase, which limits them to about 0.8 to 3 solar masses. So, which we can compare to the main sequence stars on the among the solar-like stars, plus the A and F stars. The mechanism is simply mass loss and interaction that then will subtract them from the red giant binary sample.
Milena, quick question.
Thank you. I'm also a bit confused about stellar winds and some different phases of the evolution. Could you comment on that? Are we there yet? I mean, like, is the red giants that you are talking about, they can lost some mass also with the stellar winds, right? Or...
Indeed, the stellar wind loss is about 10% of the stellar mass for stars lower than 2 solar masses. That's at the tip of the giant branch. We see significant mass loss through wind, but it will not destroy the full binary sample.
Okay, I don't see any more questions. So let's thank Paul again. Thank you very much. And we stay within binaries.
but we have a remote talk, so I'll stop sharing.
Hello.
Are you there? Yeah, can you start
Should
sharing?
Yeah, I will share my screen. And can you see my screen now?
Yeah, can you start full screen?
How do I do the full screen thing? Let me.
The slideshow.
Okay. Oh, you mean the slideshow? Okay, yeah, perfect. Okay. So is it okay now?
Yeah, you're good to go.
Okay. Okay, cool. I'm going to start now. And hello, everyone. I'm Yi, and I am a PhD student at University of Exeter, and I'm also going to join ESO's office in Santiago in a couple of weeks to continue my PhD study. And I would like to express my appreciation for the community to offer me the opportunity to present my work. And you can see from my title here, I'm going to talk about how we calibrate the astroseismology scaling relations by interferometric observation on the Gaia binaries. And when we talk about astroseismology, we know that it is the study of the internal structure of a star by studying their oscillations. And there has been several successful space missions like Corot, Kepler, and TESS that has shown that seismology do have a good potential to provide the mass measurements. And to provide the mass measurements for a large sample, one of the most common methods is the so-called scaling relation. Like the one here, I have put the most original form of the scaling relation. But the scaling relation is actually based on the assumption that all the stars have a similar internal structure to the sun. But we know this is not true, that stars do have different masses, temperatures, and metallicities compared with the sun. So a natural question would come to us is that what consequence will this lead to? So it has been reported by several studies that astroseismology do show a mass overestimation. And as shown on the left-hand side, where you can see that in this example, we show there has been an astroseismic mass overestimation. And in this study, it has been reported for overestimation for around 15%. And several different independent research has all reported a mass overestimation that is as large as 10%, more than 10%. Another consequence this would lead to is as shown on the right-hand side, where the mass overestimation might lead to an age underestimation. You can see that the y-axis here is the astroseismic mass, and the x-axis is how much the mass has been overestimated by seismology. The gray scales here represents how much the age would be underestimated. And we can see that it could be as large as 14 gig years. So we say that it's super huge, that we could not ignore this effect. Besides, another consequence we might have is that when we are trying to use the seismic mass to interpret the galactic population study, it might overpredict the number of the high mass stars. So we see that it is important for us to calibrate the model-independent masses, calibrate the scaling relations using the model-independent mass. And however, at the moment, there are only 17 of the eclipsing binaries that host an oscillating red giant has been used as the scaling relation calibrator, and all of them has been shown on the left-hand side. This method currently, as shown on the distribution, could only provide the calibrators with a nearly age on inclination and with shorter period, that is, and they prefer to have calibrators with shorter period. Besides, this method generally requires a long-term monitoring, so it's not very efficient and could not provide targets at other evolutionary phases than the red giant branch. When we are trying to calibrate the scaling relations, some most common research like the derive an alternative reference value or reference function, this kind of calibration could only work within the certain parameter space that has been derived for. It could not be extrapolated to the other parameter spaces. So we see that we definitely want some methods that could provide the calibrator that is more diverse in the sample and also be more efficient. And this is what our Gaia interferometric method could provide. So the story starts from Gaia DS3, where Gaia released its very first non-single star catalog. And limited by the angular resolution of Gaia, it would not be able to spatially resolve most of the candidates. And it would instead only provide the photosynthetic orbits, as shown at the bottom. This kind of photocenter orbits actually face a stellar flux ratio and separation degeneracy because they are incomplete, which means that we could not know the exact position and dynamical mass for both the primary and the secondary. But we are lucky enough that interferometry could break this degeneracy with a single pointing around 30 minutes. And by combining the Gaia photocenter orbits together with the interferometric observation, we will be able to derive the dynamical masses, precision edges, and full 3D orbits for both components in a more efficient way. And I am carrying out my survey on both VLTI on the southern hemisphere and the Chara array on the northern hemisphere. So here is a slide to introduce our observation. On the right-hand side is how the fringes looks like on a Gaia binary with a Chara Marcax instrument. Because Chara has 6 different telescopes, which means that we have 15 different combination of 2 telescopes that corresponds to 15 different frequencies. And that's why we have 15 channels simultaneously. And the waterfall plots here are actually the timely representation of the intensity. So you can treat it as how the intensity looks like as a function of time. And because on Gaia binary, we rely more on the closure phases rather than the well-calibrated visibilities, which means that to save more time for the sense target, we would actually record longer on the sense targets. So on Chara, we record 1 calibrated source for every 3 to 4 targets. And on VLTI, we also record a longer frame on the sense targets rather than the calibrator. And so when we are trying to do the do the modeling, we are using the PMOIRAD Python package written by Anton Morau. And on the left-hand side is a grid with chi-square grid map that when we are searching for the global minimization, you can see that around the detection here, we managed to reduce the chi-square from almost 20 to less than 5. And on the right-hand side is how the observables plotted along with the best fit models and the residuals. So what Gaia photocenter orbits could provide us is the shape of the orbit, and what interferometry could provide us is the semi-major axis and the flux ratio. So we now have the scale of the orbit. Now we have the shape of the orbit, and we also have the scale of the orbit. It is a very straightforward for us to reproduce the orbit. We first do a nonlinear least square fitting for the chi-square minimization, and then we explore the posterior distributions with the MCMC routine. And on the left-hand side is an example fit from our pilot study, where you can see that the red dotted orbits is the photocenter orbits from Gaia, and the gray shaded region is a region where Gaia predicts the secondary should locate at. And of course, the black dot here is the detection, and the group of the green orbits here are the randomly generated binary orbits during our posterior distribution. So you can see that the thickness of the orbits around the detection is very low, which means that this part of the orbit is well constrained. So in total, that our Gaia interferometric method could deal with 2 kinds of Gaia binaries. For the first one, Gaia also provides the SB1 information. We will be able to separate the masses for the primary and the secondary very easily. And for those that Gaia only provide astrometric orbits, we can still derive the masses for the primary and the secondary by extrapolating the flux ratio to the Gaia bands. And here are some statistics. You can see that the current typical mass uncertainty we achieved for our pilot study is around 4 to 5%. And there are still some potential to improve the precision in the near future, like the upcoming Gaia 4 in next year, and also that currently we are carrying out our interferometric observation in H band and K band. But since later this year on Chara and earlier next year on VLTI, we will be able to carry out our survey on both on G band, which is closer to the Gaia band. And we are also looking forward to improve our modeling and quantifying for some observational bias. So in the end, we hope to achieve a percentage error for around 2%. And here a comparison for the dynamical mass derived from our study and the scaling relation mass from AstroSeismic. And I am using the reference value that is based on from a study totally based on the red giant branch stars. So you can see that for the red giant branch stars shown here on the plot, they kind of agree with each other, but not necessarily show a mass overestimation. I think because if we take into consideration that the overestimation conclusion is only based on a very small sample of 17 different stars. So once we have a larger sample size, we could revisit this conclusion to say if there is indeed an overestimation. And also you see that for the two subjects here, they show a larger mass disagreement between seismology and dynamical mass. So I think this is as expected because they are subgiants, not red giant stars. And for the yellow target here, it is a very interesting target that has a new mass that is almost identical to the Sun. So that's why the scaling relation mass I derived is very unrealistic, and instead I plotted the modeling mass of it here on the plot. And I just want to make a quick advertisement that by the end of this year, we will be able to provide the very first sample of around 10 scaling relation calibrators as the mean sequence and subgiants. So this would be the very first calibration for the scaling relation on this evolutionary phases. So if you're interested, please stay tuned. And here is just an updated version about the compared with the previously known calibrators in the literature. You can see that even now we just have 11 new interferometric sample. We have already enlarged the sample and also enlarged the sample with longer period. Besides, we have the sample with different inclination for the first time. And by the end of the study, when we are trying to select our samples, we are trying to make a sample that is well distributed in both the space of the inclination and the period. So currently we have recorded for 70 of the targets so far, with more to come in the near future. And our method provides for the first time the calibrators on the mean sequence, red clamps and subgiants. Besides, even for the red giant branch stars, we are able to provide the red calibrators that has a larger diversity in the different parameters. So once we have our derived dynamical masses, we're looking forward to derive our reference value and functions for the different parameter spaces and try to compare the different correction methods. So in the end, we hope to, by working with the series, to calibrate the evolutionary tracks and models. And for some selected sample, we are looking forward to perform a simultaneously modeling based on both the binarity, astroseismology, and spectroscopy. So just a quick slide that I want to mention that I am collaborating with Paul on the Plato binary sense calibration and validation targets with a sample selected from Gaia. And we are looking forward to start the preparation before the launch of Plato, and derive the dynamical mass for some of the targets already, so that once we have the first data from Plato, we will be able to perform this study. And I don't have time for this slide, so I will skip it. I just want to mention that seismology provides the stellar masses for a large sample, but they need calibration. But currently, we have only 17 of the active piecing binaries with an oscillating red giant has been used as a calibrator. So our Gaia interferometric method is increasing the sample size and its diversity. And for the next step, we are also looking forward to do some age estimation. And we also have some data for the other Gaia binaries like the Melper stars and the purely red giant branch stars. So if you are interested in any of the sense case I mentioned, please feel free to contact me. Thank you for your attention.
I do the clapping on behalf of everyone so that you can see it. Are there questions to you? I just have a quick one. So with Chara, you're limited to very bright targets, but VLTI is improving its capabilities, right? Reaching fainter. Are you looking forward to that? Are you thinking about using that feature?
Yes. So actually, yes, I think you are right that Chara has a limitation that it could be only limited to like 70.5 in K or H band magnitude. But the good points of Chara is that the first thing is that most of the Kepler field is not observable by VLTI because it's a northern hemisphere. So and Kepler has a better quality of the astroseismic data, and also Chara has a better resolution compared with VLTI. But I am carrying out my survey in parallel on both Chara and VLTI. So yes, even that for my targets here, I have presented included in my presentation. It's from Chara observation, but I have already gained some data from gravity, which is gravity instrument on VLTI. Besides that, by the beginning of next year, there would be a new visitor instrument called ASCAT Bifrost by our accelerator groups that would be operational on VLTI that observing G band, which is closer to the Gaia band. So I'm also looking forward to use Bifrost to observe for some of the selected targets because yes, with the because in G band the expected precision we could achieve would be better compared with current K band. So yes, I'm carrying out my survey on both Chara and VLTI to have a more like how to say that word, more complete sample. Yeah.
Hannes.
Yeah.
Yeah, thanks. This is Johannes Salman from ESA. Very nice, thank you. I saw that you mentioned the dynamical masses to 4 to 5% for the moment, yes. And you showed the 4 options for improvements. In the current situation, what is usually the dominant source for uncertainty? What out of these 4, what is the biggest contributor to this 4 or 5%?
Yes, let me just go back to my slide. Yes, I think it would be like for the first 2. The first thing is that because Gaia DR4 will release the epoch astrometry, for which we will be able to including both the epoch astrometry with our interferometric observation. So and so this would be like we think it would be improve it. And also that Gaia DR4 will have a longer time compared with a longer observation time, because currently we found that in practice, sometimes when we have the binary or period that is longer than 1,000 days, it could have a super large uncertainty predicted by Gaia. But I think once we have DR4, we will be able to have a better uncertainty that is with additional Gaia data. And I think that is a good news to our study, because if once the Gaia DR4 has been released, we do not need to carry out our observation, but we could use the data we already have to compare with Gaia DR4 to have an improved precision. And also, I think maybe the second one is the observation band, because like for those that we Gaia do not provide SB1 information, we rely on some flex ratio extrapolation. And from our simulation is that once we carry out in our observation in G band, it could reduce our uncertainty further. So I think the first 2 would be the dominant 2. Yeah.
Thank you.
Thank you.
Thank you very much. Thank you, Yi. If you could share the screen, we clap and thank again.
Thank you very much.
Thank you. And now I invite Edita Stonkute. And this is the bank. Works. We'll stay within the binaries, but we'll move us to spectroscopy, right? Use this or just space.
So good day, everyone. As Lucas presented, I am Edita Stonkute from Vilnius University, Lithuania. And I'm here to thank, until my presentation run out of time, to Gaia team, as well as BH-TOM network, every one of you, including my colleagues in Lithuania, Marius, that he could not be here today, and he is sending greetings to everyone who knows Marius. Colleagues from Vilnius University who are here, and also our colleagues in Poland. We are running a project that called Polish-Lithuanian Black Hole Hunt, and we name it Next Round Harvest Time, because we can use Gaia to identify those dark objects thanks to microlensing events and Gaia alerts. And what about those dark objects? We are trying to figure out and derive derive what kind of sources are hidden in our galaxy. And it's not only efficient to have only photometric or astrometry data before Gaia, there are 4 and there are 5, we also sometimes need spectroscopy. And today I already heard several times mentioning that as much information, as much data we need to resolve the degeneracies in lens parameters, and the spectroscopic data actually holds this potential. And we know that on the sky, we have a lot of spectroscopic surveys, and they have their archives. Probably we have to go back and look at those archives. Can our favorite target be in those archives? Can it help us? And today I looked at the spectrographs that we used for microlensing events. And nice if we have Gaia RWS spectra. And I show you here a nice image from a nice figure from Alexandra Reza Blanco paper on Gaia DR3, where many stars have their parameters determined from Gaia spectra, Gaia RWS spectra. But for microlensing events, we want to have a quick look what kind of object we are dealing with. So we don't need extremely good resolution. So low resolution spectra like Liverpool telescope Spratt spectrograph can give us is sufficient enough to figure out what kind of object we are dealing. If it's a transient object, if the anomaly is due to something which we are expecting, or we can use higher resolution spectra. So Pavel is working on many of those spectrographs, applying for many of those spectrographs to get time, like X-Shooter, SALT, Gemini, Pepsi, with extremely high resolutions. And if you want to look at the results, there are many papers written by Bechtom people. I listed several of them, recent ones, where we figuring out those dark objects in Milky Way. And if we look at the current facilities and what is the next generation spectroscopy look like, you see the figure from Magrini paper where she plotted on x-axis resolving power and on y-axis the number of fibers. We see that the top bubbles are coming from the future facilities. Probably you cannot read the facility names here, but I will talk about few of them. And the smallest and lowest fiber number and in resolving power are current facilities that we have spectra and spectrograph. And also when we deal with targets, microlens for objects, we usually deal with faint objects. And if we want to know the source star and parameters of the source star, we can use Gaia DR3. But as you can see, Gaia DR3 peaks around 12, 13 magnitude. And if your object is fainter than that, we might want to look in other surveys. And here you see that fainter objects could be found in Apogee, Gala, or guess surveys. All data are public. And I choose two current surveys that are still running to present you. One of them is in the southern hemisphere. It's Gala survey with Hermes spectrograph. It's a almost 4 meter telescope in Australia with 400 fibers, and the magnitude limit is around 14, 15. And it has 4 optical windows and quite good resolution of 28,000. And Gala DR4 data is public. It was released last year. It's around 1 million stars, 1 million stars with derived atmospheric parameters with spectra. You can take spectra and use yourself for your science. And if you want to use and look at Gala data, you should be looking for Gala All-Star catalog that I listed here. And what is nice with Gala that they also have a phase of faint targets in the galactic bulge that is shown here in orange. So if you're looking for your targets in the galactic bulge, maybe Gala is catalog to look at the spectroscopic information on your target. What is not beneficial to time domain for Gala, that Gala observes a target usually once, and it's not multi-visit observations. But what is good with Gala, that it cross-match catalogs with DR3, Gaia DR3, as well as with 2MASS and WISE. And this is very important for us when we want to look for our targets. So if I would have a right to suggest to surveys, I would ask all surveys use one identifier that we could look for our objects and easily find in all those different surveys. And I would say, let's all use Gaia identifiers for each survey. That would help. And another spectroscopic survey that I wanted to present is LAMOST. LAMOST is in Northern Hemisphere. It's a Chinese project. And they're running for many years now, and they have 20 million spectra of objects. Both they are observing galaxies and Milky Way stars. And it's amazing. They have 4,000 fibers on 4-meter telescope. And the limiting magnitude is 19 in airband. And even though resolution is not too high, 1,800, it's still very, very good. And if you look at the skeleton of the telescope, so it's 2 telescopes, 4-meter, 37 segments dish as a primary mirror, and then there's another one, and then in the middle we have focal plane with 4,000 fibers, 16 spectrographs, and 32 CCD. So it's really amazing. And they also have data releases. Now the public data release is number 10, and they also have internal data releases with internal collaborators. LAMOS data is very popular, as they say in their page. And if you want to look at the LAMOS data, you just go and see. You can even quick look at the spectra. In their archive. The spectra is very interactive. You can also see the lines if your spectra is showing any emission or so. But good with LAMOS is that they have multiple visits. So you can use this LAMOS archive for time domain. And last but not least, what kind of panorama as awaits for next generation spectroscopy? I will skip Andes on ELT, but present a quite new thing is MOONS. MOONS will be on VLT, and it will have around 1,000 fibers. It's optical near-infrared region, and with 3 different resolutions. And it's planned on Sky to be pretty soon. And it will provide deep spectroscopic follow-up of current and future optical and near-infrared imaging surveys, as listed here, VISTA with Pan-STAR LSST, and space missions as well. And the power of MOONS will be that it will observe quite faint objects in the Milky Way galaxy, and we will be able to see stars in bulge and globular clusters, as well as in disk, and characterize them. As well, MOONS will be able to look at different redshift galaxies. And one more project that is under submission is HRMOS. It is high resolution multi-object spectrograph planned for BLT. If you want to know more about HRMOS, I refer to Magrinis white papers 2023. So it is new flames as we want, and it will have exquisite resolution up to 80,000. It will not have many fibers, but it will be probably quite many anyway. And if you are interested in new facilities, new facilities for the spectroscopy, I refer you to sign up to be in the consortium of Foremost scientific consortium. And the last, probably a game changer in astrophysics might be WST, Wide Field Spectroscopic Telescope. And they recently published the Chronicle. This project is planned to get first light if it gets funded around the same time as ELT, and it will be a project on dedicated 10-12 meter telescope, and it planned to work together as multi-object spectroscopy and integrated field spectroscopy simultaneously. And it will have, the project is that it will have enormous number of fibers, 20,000 and 2,000 for low resolution and high resolution. So I also invite you to join science team and to learn more about this game changer in astrophysics. So thank you for listening. And in Lithuania, we have already winter and it's like +6 degrees today. So
Thank you very much, Edita. So it's good you were able to escape from winter to here. Questions to Edita? David.
Just a comment. Oh, David Buckley from the South African Astronomical Observatory. Just a comment on the WST, that is a proposal, I think, for ESO. But maybe in this context, you should also mention the Time Domain Telescope, which is an alternative in competition, I think, with WST, with the idea of multiplexing many telescopes, small aperture telescopes, with fiber-fed spectrographs. It's something which Paul Krut, I think, is the person pushing this project, but with a number of people interested in time domain astronomy, also interested to push this.
Do you remember the name? Okay.
TDT, Time Domain Telescope.
Okay. Thanks for this. Piero.
So I think just a correction that this is not like ELT time. This is really far from ELT. It's like 2040s plus what we are talking about in case of this projects. 2040 plus, because you said that it's like a ELT, the same time as ELT, but it will not happen at the, definitely not happen at the same time, because ELT is almost built. This one is on the paper yet.
Yeah.
And
way after ELT.
And if I can, there is no other question. No, I will use the privilege of holding the microphone. So I think that the proposal for having the same identifier is interesting, but I cannot see any way how you can actually manage that. So if you have an idea, give this to astronomical community, and I think the astronomical community will use that. But using Gaia will not work, given that you have different spatial resolutions, right? So you have 3 sources, 10 sources for one 2-mass source, for example. So you cannot do that in this way. So if you have some other idea, I think it will be great.
Michel?
While we are talking about future project, there is a project similar to the WST, but for the Northern Hemisphere, which is the Mauna Kea Spectroscopic Explorer, which is to replace the 3.6 meter in the same dome at a scale with time scale, which is not clear because, as you know, the situation in Mauna Kea is quite difficult these times. But it's the plan to replace the 3.6 by a 10 meter telescope, wide field spectroscopic explorer. funding is not complete. So if you have money, you are welcome.
Oh. Okay, I don't see any more questions. So let's thank Edita. Thank you very much. And so now it's time for a coffee break, but the coffee break will be sponsored today by BH Dom. So if you see some Polish sweets on the table, think about BH Dom and contribute to BH Dom. So this is the most exquisite Polish sweets, which we call in Polish it ptasie mleczko, which is direct translation bird's milk. So you can blame that we brought some bird's milk to the Canaries because we thought this is all about Canaries, the birds, and it turns out to be dogs. So it has to be eaten. So we'll move it on the table. And let's meet here at 3:45. Thank you.
And during the coffee break, we will have posters displayed on the screens. So we will be running the posters. Every poster has a slot as a post talk. So you will hear also the talks. They are in the schedule, so you will find them. But during this coffee break, from this coffee break on, we will be showing them on the screen.
So if your poster is displayed, then hang around here so
That's
people read it.
That's not
and then they can discuss your poster. Okay, thank you. No, chyba jest programu. Nie ma. On jest ze mną spisany za tokiem. Tak. Się wydaje, że go wpisywałem. Nie ma go. No to spoko. Mamy miejsce. O, tu zostało już zmienione, ale tutaj mamy miejsce. A to ciekawe, że gdzieś zginął. Wiesz co, o czym ma?
O tym OCS-ie naszym, czyli implementacji OCS-a naszego. Wiesz, nie ma ciśnienia, nie?
Nie, ale to właśnie koło twojego toka, wiesz, wciśniemy go. Tutaj, bo tu nam się zwolniło troszkę.
No to może być po moim toku nawet. To ja
Albo po
powiem,
twoim.
Wiesz, coś tam powiem i on...
To w ogóle zróbmy tak, że ja wam zrobię 20 minut już. Po prostu.
Okej.
Tak? Tak, żeby będzie to jakby was jeden wspólny tok.
Dobra.
Łatwiej mi tak niż przesuwać. Albo po prostu, ponieważ jesteście dwóch, to po prostu wymieńcie się w którymś momencie, slajdy prześlijcie odpowiednio, nie?
Dobra.
Dobrze, a ja tu dodam więcej czasu.
Dobra.
No to nie wiem, jak on mógł zginąć, ten tok. Raczej, chyba że późno zgłosił. Bardzo późno. Okej. Jest, myślę. Yeah. Sure. So the talk now in this session, it's Tapio giving it or you? Tapio this time. Yeah, so feel free to expand your talk. I'll give you more time. Okay. No problem. Yeah. Yeah, definitely. Yes.
Sure. Wiesz co, biedy można spróbować swój podłączyć.
Bo wszyscy z tego pokazują, albo trzymam kursorem tutaj
Tak, widać go.
Tak, wskaźnik, ale na tym nie działa.
Nie, kursorem lepiej, bo wtedy widać online też. No. Dobra. Oh, good. Yes.
Having a bit of an issue with the male's restroom.
Why?
Wash your hands. Underneath that, there is like a piece that apparently, I don't know, it's loose or something. Let's see.
Yeah, you know Pablo already, no?
Not yet?
No, not yet.
Working beside the sunset.
Mhm.
And I'm responsible for like nation operation storage.
Great.
And the other thing is how to put on time stage for the power.
Okay.
Yeah, I'm doing the board stuff.
Oh, wow. Yeah, I have to do both. Yeah, cool. Cool. Yeah, I'm looking forward to that. Yeah. Just, yeah, we're on this time. Yeah. Yeah, I'm actually related to both of you. Yeah. This is like permanent.
Yeah, so, you know,
Yeah, that is, so there will be a huge amount of sun, but the plan is all sense. For the body and by.
Yeah, so that's my idea. But I think he's coming from that different way now, right?
Yes.
Yeah.
He's like, it's like those public.
Yeah, exactly.
and then I think, you know, the sign. Some points very bad. Okay. So this is not big. Because okay, good. But we could have a look if, you know, if you kind of stuff together, I can probably.
Yeah, that's all my main question, whether all the optical have to do with here and follow-ups and feedback kits as well. Yeah, let's stop, definitely.
This will take 10 seconds. This talk by Sophia.
Mm-hmm.
She will give from her laptop.
No, I think it works.
No, we tested it and she has some animation thingy because you don't have PowerPoint.
But it opens in Keynote.
It opens, but it messes up like it overlaps the text.
Fixed. Okay, yeah, I see a bit messed up. Yeah. Sweet.
Yeah.
So
she will put her laptop here.
Okay, that's good.
We try to get people to the PDF, but also people still
Right,
don't want to do it.
right,
So.
right. But yeah, that's all she needs, right? I just need to unshare the screen so she can share it. So she has to connect to Zoom, right?
Yes, she'll be already in the Zoom. No, I'm just saying, she'll need the space for her laptop.
Yeah. Okay.
Maybe it's
Yeah.
So we don't want to touch this too much.
Yeah, I'll leave it now. Okay, good. Hi, Tapio.
Hello.
Hey. Good to see you again.
Yeah. So this is the interface for the talk.
This is the interface, and I got your talk.
So you just press the arrow key to get to the next page.
Yeah, perfect. Yeah, or you can use some more fancy tools. Okay.
I'm old.
No,
Old school.
Old school. Well, this is more robust than this. Yeah, so your talk is here. It's a PDF, so that should work.
Perfect.
Cool. Right.
Impressive facilities, yeah.
Yeah, it is. We're working with the other island.
Yeah.
Cool.
Wow. Payday every month. So
But so do you have a new director now?
yeah.
Who's the new director?
Petri Raiden.
Petri Raiden. Yes,
He's also part-time.
He's part.
He's a director of Kingdom when he needs digging and then do part-time with our.
I see. Yeah, I remember. Yeah, I know that spectroscopy is a key factor in NOC, but I was thinking about the imaging for everything. Yeah, but I was thinking about imaging using NOC for imaging Yeah, occasionally, right?
Yeah, you're very welcome to.
But then, yeah, in order to get time, it's difficult.
If you have money.
Yeah, exactly, I can buy them, right?
Oh, I mean, yeah, it's the same, but there's no more become.
Yeah, exactly.
That was very nice. And money. And of course, more users and
Yeah, I started talking about this with the format director, Thomas, yeah, that we could have some connection between Tommy with our wisdom and not, and the connection to automatize things, and we could also reprocess some of the archival images. So I don't know if this is still possible to talk about this. Should I get back here about this, you think?
we are working, like we are part of all of the song and other things. They have money and they are building the archive for Warsaw and from the side not in that thing that
okay, so who's leading that?
More good. Song is Max something.
Max. Yeah, I know Max.
Max.
Yeah, I think I know. Yeah, because this is something that is in my mind for a long time. Then with the turbulence with the director and all stuff, but
yeah,
but
yeah, you had some sort of with the EU proposal.
Yeah, we had applied last year, yes, but we didn't get it. So
yeah,
I'm sorry, we have to start now.
Yeah,
but I'll get back to that topic. Yeah. We're about to begin the afternoon session. Can I get the screen back? Anna, can I get the screen back? For people on YouTube, so that you see what I was using. Oh. Yeah, will you use it?
Oh, I'm gonna have
You
to.
missed it. That's a new one.
There was a new one in Crete. Is it a new
Yeah,
one?
it's the same. Okay. So we begin with an invited speaker and part of our walk. So the organizing committee, Simon Hodgkin.
Thank you very much. I didn't invite myself, kind of. I hope you can hear me online. Thank you very much for having me. It's wonderful to be back in Tenerife. It always is. So I'm going to whiz through what we've been doing for the last 10.5 years, although as Łukasz correctly pointed out, we've been doing this since 2010. Yeah, so a lot longer. And it's wrapping up, at least this part, the delivery of the transients is wrapping up. The delivery of the transients is wrapping up. Now I'll stay put, I'll just bend it down a bit. And so I'm just going to give a quick summary, brief overview of, now I've got too many. A quick overview of what these last 10.5 years have been like. And so why did we begin this project? So when we initiated it, it was really to try and keep an eye, to exploit the data that were being delivered every day. And to try and look for things that, well, this argument is serendipity is the fortunate accident of discovering something that you weren't expecting to see. And this gives us some insights. So we have periodic variables, we have things you might expect to understand, eclipsing binaries, exoplanets, examples of those, but you have accretion disk, you have microlensing, we have flaring objects, and then you can use some of these and they give you leverage so you can measure the expansion of the universe. using supernovae. And now gravitational waves, black hole mergers, neutron star mergers are giving us insights into processes in the universe. So this figure I'll come back to later, but this was the landscape of the brightness of an object against the decay time. And there are lots of areas here that were only partially filled in, hatched. One was known, a couple were known, and this was really poorly understood. And then we knew about the supernovae 1A, luminous blue variables, classical novae, so there were things that were much better understood. And so the idea here was, if you stare at space, maybe you'll find more examples of these, or maybe you fill in the parameter space and find the unexpected. So the trouble with Gaia, I'm sure most of you know, is we don't get the pixels down. We're dealing with the catalog. So we have catalog data coming down, and the sky can look quite messy to Gaia. So these are the focal plane detections of sources by Gaia around Saturn, around bright star like Sirius. And so the idea is, when is my source really a source, or when is it an artifact of the observation, of the observing system? And the bottom right example here shows you another problem, which is the initial astrometry is pretty good. It's good to 100 milliarc seconds. But if you have two objects close to each other, then which detections you ascribe to which source can lead to confusion. And we find this very early on with our transient detection system, is that sometimes the source would swap source IDs, especially if the brightness changed. So there were lots of confusion between sources. This improved a lot during the mission, and the system became a lot more robust over time. So our detection system that we were running based solely on catalog data, remember, is we asked an object to be seen in two fields of view, so two observations. And these two fields of view separated by 6 hours essentially is the rotation period, so 2 and 4 hour separation. So you want two observations within a 40-year timescale for a detection of a new source. And we need new sources to be brighter than 19th magnitude. I'm going to keep talking present tense, needed, but you get the idea. And so these new sources are transient events. So they're things that used to be too faint for Gaia, and suddenly they appear to Gaia. So we have a new star, a new source. The other kind of events we triggered on were old sources that changed brightness. We asked for a significant change in brightness. So they could get fainter or brighter. We were agnostic about the direction of flux change. And we asked them to change by a magnitude or to be a statistically significant change in brightness compared to the historical variability. And then this was Wukash insistence, we asked to be able to detect things that change brightness slowly over time to try and improve our sensitivity to microlensing events. And I was very successful at finding these things as well. So you can imagine we have 100 million transits a day, and these are measurements of Gaia, and it's scanned this strip across the sky. So we've got 100 million measurements to wade through. And so the first thing we have to do is do a data quality control, so try and work out which of these are reliable, good measurements. And then we run our detection on there to look for these things that are truly new to Gaia or have changed. And then we try and classify them, say, why did you change? What are you most likely to be? And that left us with about 1,000 valid candidates. And then we ran some filtering on those to say, what do we think the cause of this brightness change were? So we had to get rid of things that are obvious, high amplitude, long period variables, for example, is a class of the thing we try and filter and protect ourselves against, which left us 20 or 30 things to eyeball. And then about 10 a day we publish. And so we have this team of people helping us do it. In the good old days, at the end, there was only myself and Diana sort of running the system towards the end. We didn't have a neural net. We always wanted to build a neural net. Instead, we had to use a human-powered neural net, which worked pretty well. So the data rates we're dealing with, the gray curve at the top, the number of detections per day are the blue things. You see a jump around about 2020, and this is when we started detecting things only in one field of view. And we published that as noisy stream, and the argument was if it was coincident in time with something else, a gamma ray burst or a gravitational wave event, then the timing could be used very powerfully to reject garbage and use that as a strong optical counterpart. Unfortunately, we didn't overlap with any of the LIGO Virgo experiments, very few, and so there may be data in there that's valuable and useful, and that's all public as well. And then the red curve is the number of things that we had to stare at, and the black things are the number that we published on our web pages. There's this area that's called the Nightmare, which was towards the end of April 2024. There was an event where we had a micrometeorite hit with a lot of extra stray light, plus a series of solar flares, all within a short space of time, that created a lot of onboard activity for the spacecraft, you can imagine. Our system was robust against this, which I was very happy. And the data processing in general will be very robust against that when you come to see the data in the future. So it's remarkable how robust Gaia was against sort of collisions and X-ray events, from particle events. And so it's, luckily though, I'm very glad it happened late in the mission operational life. So the things we were filtering against, most of the things that cause us spurious events were because they're near bright stars. And so most of these examples I've labeled on here are things that are close to brighter stars in the field of view, or could be associated with a nearby neighbor lining up. We also got parasitic sources from the other field of view, which are superimposed on the same detector, and they can also cause brightness variations. Other things we had to protect against are known solar system objects, known variable stars. When we had catalogs of those, we used those more and more as they got released. The most pernicious in a way were very high amplitude red variable sources. So they were reasonably easy to filter out. But early on, we were erroneously publishing known variable stars, only a few, but still. And the eyeballing, this is an example of the data we had to stare at. And so we just looked for associations of where the transiting events were compared to previous measurements of the source. We looked at the light curve, and we looked at it in different orientations to try and understand if this was essentially believable. We looked at the color as well, the uncalibrated color. And then we looked at contextual information. So was it near a galaxy, or was it an isolated object, or was it very close to a known object? So we used all this contextual information to try and help make a judgment. You can see in the bottom right, just hidden, we also use the BP-RP spectra. And you see there's a little bit there in the RP, the red spectrum. Is there a laser? No. Okay, it works on that screen. So for those online, around about pixel 60, there's a little bump, and that's H-alpha emission. And so things like this gave us insights into the color of the source. I can see it's very red. I can see it has H-alpha emission. So the eyeballing led us to publish about 27,000 alerts over this 10.5 years with no boom. Okay, hopefully you can still hear me online. And so we had periods of operation where our system got stressed. So where our database got too full, because we built a system that would run for 5.5 years. We had to operate it for 10.5 years with the same hardware. So we had to sort of refactor our database and do things that we were essentially not prepared to do, didn't know how to do it, running on fumes, low on human resources. So it made it a tricky problem. But we managed to keep going to the end. So the patient was sick, but still on. That's helpful. And still on life support. So of the published alerts, so 27,000, we managed to classify 28% of them. I say we, that's in the loosest possible terms. A lot of people are doing a lot of follow-up work, and a lot of our events were observed by other projects as well. So they're not just found by Gaia, a lot of overlap. So about a third almost of them, 28% were classified. Couple of points on the photometry. The calibration was pretty stable. So a 19th magnitude, our photometry was accurate to 3%. Sorry, precise to 3%. The accuracy is debatable, how you calibrate your filters and all of that. And 1% of 15th mag, that's pretty good. However, we stopped calibrating, measuring the calibration, sort of 3.5 years before we finished processing systems, but the calibration stayed remarkably stable throughout the period. So the calibration is never, ever meant to be as good as what's released in Gaia data releases. And so that's the first point is a year and a bit from now, you will get all the first 5.5 years of data with Gaia fully calibrated, the spectra as well, to millimag precision or better for the photometry. So you can repeat this exercise and do it properly and find all the things that we missed, because the trouble with running a system in real time is you're always trying to stay up with it. You develop a system, you have to run it. You don't have time to redo it. And so there is now time to redo it. So if you really want to measure the completeness of the system, you can do that. And if you want to measure supernova event rates, you can do it. You can do all of this much, much better than we were able to do, except the events have been and gone. So you'll have to kind of work out how to work out what they were. But I think you can do that. The astrometry was good to 55 milliarc seconds. And so everything we detected with Gaia has been used by transient name server as the sort of ground truth for astrometry for all the other missions. And there's a lot of comparison between the other surveys that were running simultaneously to show that the Gaia astrometry was really very good. So now I'm going to talk about where our events were on the sky. So you can see in the top left that the Gaia events were uniformly, well, not uniformly, but were distributed across the whole sky, as was Saturn. But Atlas and ZTF ran through these sort of galactic plane avoidance, crowding, for very good reasons. But Assassin, like us, were not frightened of the galactic plane, and so went where others feared to tread. So of the 28% that were classified, then 74, 3/4 of them were supernovae, and then broken down to AGN, then CVs, and then YSOs in that order of frequency. But we have to appreciate that the reason supernovae dominate is because there's a team of people who love supernovae and have nothing better to do than take spectra of every single supernovae, because each one is special and rare and to be treasured and teaches you the size of the universe, and lots of very good reasons for doing that. Whereas the other classes didn't get so much love or appreciation. And so it's only thanks to Michel and other people around that people looked at these other things and these rare creatures, and they got the attention they also deserve, but not quite as much as the supernova community's kind of motivation or time allocation. So this is the distribution of classified alerts on the sky. And so you see that the classification frequency is, there's some overdensities that you can correlate with known star forming regions for one. There's an example of Orion. And there's seems to be sort of doing better at higher latitudes than lower latitudes. And for the unclassified alert, then we're really dominated by the galactic plane. So there's a lot of things happening in our own galaxy that are not known or understood or being chased. And so that to me was quite interesting, and it's going to be very interesting for these upcoming transient surveys and how they're going to manage this this largely unknown population. And so this is just to show the different classifications of those, and I won't go through it now, but definitely in Orion, you can see bottom left, all the blue things are YSOs, and there's an overdensity of YSO detections around Orion, which is quite interesting. I put a blue question mark because there seemed to be an overdensity of supernovae in that direction. I don't know why that should be, and I find that quite interesting, but to be understood. So that's just reiterating the point. So this is building on something that Laurent showed us earlier, which is really interesting to look at the color evolution of different sources of variable, different classes of variables. And so there's some examples here. These are uncalibrated colors, uncalibrated photometry, but we put the absolute G-band magnitude using the parallaxes from DR2, which is what we had at the time, but our uncalibrated BPRP. But you can see the different classes of source sit in different places, but also do different work. walks. So why I'm flagging this is when we get DR4, you can do that for every single source in the sky. And so you can then start to group things. And I think that would be a really, really exciting project to do in about 13 months time or 14 months time or whatever. Don't even know what month it is, 15 months time. So so this ability to classify based on variability and color variability is going to be really powerful. We tried to do it, and we did an okay job. And so this was led by Morgan Fraser, and we put it in our paper. And so we were able to find a bunch of new candidates, cataclysmic variables, and separate them from young stars. So we just did a simple CV or YSO kind of classification. And then Mystery et al. Did this much better, and they used a lot more parameters, and they used, I think it was Gaia DR2, I think it would have been then, to use the parallaxes in there as well, and a lot of other parameters that we didn't put in, and they put in new classes as well, and they came up with almost an order of magnitude more classified sources. And so it's a really nice piece of work and shows the future for younger generations. Machine learning can be your friend, can be a very powerful tool. You can do a lot with it, and you find things that look like things in this multi-dimensional parameter space, and it's a very good way to pull out classes and to give you probabilities for them as well. So if you've got very high probability, you'll spend more time following it up. So the paper's published today, so I made this only a day or so ago. So it's steadily increasing. It's quite interesting that the differential one is reasonably flat, which is nice to see. And so the number of papers cited this paper of mine, which came much too late in the project. If I published it earlier, we would have got more citations, but there you go. But I think that's indicative that people are doing amazing work and using the alerts, which is very rewarding. And in part, that's thanks to these meetings, series of meetings. So thanks to everyone who's been involved over the years, but especially Łukasz for bringing this community together, which is a really inspiring community. And the talks today have been phenomenal. I've really enjoyed all of them, which is why I keep asking irritating questions. And this network of telescopes that you've built and to connect and to enable this kind of follow-up is remarkable and to be fully commended. So that's the network. It's probably been updated. This is a year or so old. So a couple of comments. One, detection is fine, but if you have the blue dots, which are Gaia, it tells you nothing. And it's only thanks to the follow-up where you've got these multicolored dots that you can start to really classify it. And if the cadence is high enough and multi-band, then you can model it. You can really understand what it is you're looking at and do the physics and solve for the system, solve for the masses of it, and find it's a binary event. But the Gaia data alone are not good enough to tell you that. You will never understand it without having the commitment to do the hard work, which and the amount of work here is incredible. A huge amount of observations. And we got amazing insights as well. There's a source here that the event, this is a young star, and it's an FU Orionis outburst, probably. And it started outside in the disk because we saw it brighten in WISE before we saw it in Gaia. So it tells you about the temperature distribution of the emitting region. We also measured an improved galactic nova rate, which is from Adam Kawash. And so you see the last two data points there are based on Gaia. Well, the pink one's based on Gaia. So it's the largest sample to date, and that included a lot of detection from Gaia for galactic novae, which is very nice. And you see the error bars are much smaller because there are more events. So it gives us more confirmation of what the true nova rate should be. So I'm not going to show this movie again because I'm running out of time. So earlier, but I am going to make a comment. So these extreme nuclear transients. So in the movie, as it got brighter, it also got significantly bluer. So the argument is this is a tidal disruption of an intermediate mass star. And there are 3 such events, 2 of which we discovered with Gaia. And it's only because, well, this what is worth showing. It's only because we had this incredibly long baseline that we were able to not just trigger on it, but follow the evolution, which means you can model it. So that's the first comment. The other comment is they this system, Hinkle and Co. triggered all their follow-up of these objects and objects like them. And these were the two from Gaia plus one other that they ended up classifying. But there are two other papers on these class of events. So extreme nuclear transients, to me, were new. I wasn't expecting Gaia to make these new discoveries in the last year. So it's very rewarding that these have come out, and they sit above and to the right of everything else. And they've been hiding in plain view, and we didn't know. So thank you, everyone, for the work you've been doing. The amazing science using the alerts we publish make it very rewarding. These are just numbers. I'll spare you all the numbers, and I'll leave with a movie. DR4 is going to be incredible. You can go and do all your transient astronomy all over again, but not in real time this time. So I point you to the paper, thank and acknowledge a lot of people, which will be on the slides, and I'm going to leave a movie playing and take some questions. Thank you very much.
Thank you, Simon. We have time for some questions. Milena.
Thank you. Congratulations. So since it's done, so congratulations on the great work that you have been also leading, co-leading. So it's great to see all the results and that the science that comes after all this Gaia science alerts. I was wondering if there's any lessons learned that you can actually pass through the community that's gonna work on alerts from LSST or something like this, or for, I don't know, like future missions also, like Roman or something like this, because it's been a tremendous work that you were doing, and I'm sure there's some things that worked really well, and over 10 or dozen of years, you have some probably lessons learned that could be passed. What would that be?
That's a really good question. I deliberately didn't talk about any of those things because they're quite technical. So one of them is you're going to need a bigger database. So I really like the CU7's approach to their database, which is to go for multiple databases that can operate in parallel. And we put all our eggs in one basket, and that was a bit short-sighted. Another would be the way we handled the objects was naive. We used the source identification provided by Gaia under the assumption it would never change, which was wrong. And so then our indexing, when we had to rebuild our database every time the catalog was updated, which was 4 times over the period of operations, which lost us a month while we rebuilt our database. And again, having a bigger, quicker database would have made that whole process quicker. So some things we baked in, our early design of the software came back to bite us, and we hadn't appreciated the issues. Everybody else out there is a lot smarter and wouldn't do such naive assumptions, but we made some mistakes, yeah.
But on the excuse side, it was 2010 when we had to come up with the ideas which would be valid then in 2025. So given the technology at that time, we made some decisions, right?
Yes.
Laurent, yes.
Yes, I had the same question than Milena, but are you involved in LSST, for example?
No.
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 I had another question about the magnitude limit of 19. Have you tried to optimize why not 19.2 or 18.8?
No, that's another early decision where we chose a threshold and we stuck with it because when you're running and you're resource starved, you don't have time to do the experiments. So you just make a choice and you have to stick with it. And then you say, okay, we could go a bit fainter. So we did play with the 1x, the one field of view, and that went all the way to the limit. So that went down to 20.2 or something like that. So we did push down in this one single field of view. I'm not sure how many people used it, and I've never seen anything published from it. So so you can give the people what they want, and then maybe they're happy with their sort of vanilla product with the limits. But you saw the event we published with the light curve. This one, we triggered on it very late because it had to get brighter than 19th first, and then we needed 2 detections brighter than 19th for us to trigger. So it spent a long time rising where we had valid measurements, but we didn't alert at any point there because of these early decisions. We missed a lot.
Michelle.
Yeah, concerning the detections close to the nuclei of galaxies, there was this software developed by Susanna Kostrozeva and you and other colleagues, which from my experience seemed to be more efficient in detecting variations in close to galactic nuclei. I understand it could not be implemented because of whatever compute or power constraints or whatever, but isn't that something which should be implemented for future surveys, preferably to the method you used?
So what Michelle's referring to is exactly the problem of source identification. So I talked about the labeling of sources with new IDs. There's another thing, which is when sources are very close to each other and overlap, their transits could be assigned to a different source. Or if they change brightness, then the software at that time would decide it was a different source, even though it was within error. And so the initial data treatment early on was very, in a sense, it allowed sources to, if they change brightness, to be given a new source ID. And because all our detection was anchored to source ID, then that meant many sources missed measurements, and so we missed events. So this would be one thing I would redesign, is never use a source ID, use position. The position is so good, just do everything on position. But the same excuse is we didn't have time to stop and rewrite our software. So you either keep running it or you stop. And so we kept running it.
Okay. Thank you very much, Simon.
Thank you.
Let's thank Simon again. And now we continue on the theme of the alerts, but slightly from a different wavelength perspective, right? Tapio?
Yeah.
Want to use this or just this?
Maybe this one then.
Yeah.
When my hand is shaking then.
Okay, it's close to the mic.
Okay. Yes. Okay, hello everybody. My name is Tapio Pursimo and I'm staff astronomer at the Nordic Optical Telescope at La Palma. And this talk is subsample of Gaia alerts, and well, obvious subsample is that it's about radio detected Gaias. So my initial idea was to use NVSS survey, but then a month ago I learned that there's another one, VLAS, which is far superior to NVSS. So I took all the I started to work with the AstroPy and measured the distance between the Gaia alert coordinates to VLAS coordinates, got the distance and the position angle. And well, I forgot to say that VLAS, that's a new survey in 3. You can see the details over there. And plots or the figures, that's NVSS first and VLAS of the same target. And it's quite obvious that the VLAS is superior to the old surveys. So I started conservatively with 7 arcsecond, 7 arcsecond search radii, and I got the left-hand plot, and I noticed that, it seems that there's a concentration on the center, and I went to the zoom in, and the right-hand side, that's a 1 arcsecond distance between the optical and the radio coordinates. And well, I would say that the coincidence is fairly good. And this is the histogram of the separation of this 1 arcsecond subsample. And there's on average, the distance is about 0.25, 0.3 arcseconds. But in a separation, there's a tendency that to south, that there are more offset to south, and there would be a uniform distribution. And that was pointed out by Coron et al., who created the VLAS catalog. And from now on, I will talk about GVLAS, which is Gaia VLAS thingies. So this is the pie of the Gaia classifications. The donut shows the targets which are between 1 and 7 arcseconds, and the center is the center part. And when I took the whole lot first, there were lots of supernovas, and I was shocked that that can't be right. But luckily, on the inner part, there are hardly any supernovas, and actually, at least one of them is most likely a true coincidence. That was 2016 of supernova, and the data is from 2017. So anyway, these are the numbers. Most of the guys are identified as unknown by Simon, and the rest are AGN. And this is some numbers. This is the number of alerts on the left. That's the total number, and then the small fraction down there, that's how many have a radio counterpart. And then the red histogram shows the fraction of radio counterparts per year. And I think there's very consistent number of counterparts, so no biases over there. Actually, I got one Gaia is missing one alert. I have 75 and it should be 76. I have not a clue where it is. Then next step, I got the redshift from NED. And on the left-hand side, are the redshift distributions of different categories based on the Gaia alert classification. And the right-hand side is the NED classification. Well, there's no news over there. AGNs are at low redshift and quasars are high redshift, and then the blazars or BLAC objects are somewhere between. Then magnitudes for GVLASs. The blue one on the top top histogram. Blue one is all Gaias, and then the red one, which are slightly fainter, that's the GVLAS, and most likely the apparent brighter all candidates is because there are plenty of targets which don't have a historical magnitude. So the full sample mean magnitude or the distribution is skewed. And then just looking at the Gaia alert, alert magnitudes are the all and the GVLAS are this one here. So there's no difference between those two. And then the histogram, the blue histogram below, that's the flux density histogram of GVLASs, and the median is about 30 millijansky, which is somewhat higher than from the total VLAS flux density flux densities. Then I got the third data point to the next frequency, and this is the gamma rays. As many gamma ray optical or AGNs, they are active in or bright in gamma rays. I checked the Fermilab catalog as well. And this is the sky coverage of all the black dots are all GVLASs, and the red ones, they are those which have the gamma ray target within 6 arc minutes of the radio coordinates, which means that there is almost half of the, no, let's be conservative, 1/3 of the radioactive Gaia alerts are actually gamma ray emitters as well, which is quite a lot in reality. Then I looked at the post and pre magnitudes between these are Gaia magnitudes between the LAT detected and just the radio detected targets. And alert magnitudes is the bottom right-hand side. The gamma targets, they are on average brighter than an average radio source. And the same is with the, if get the light curve and calculate the quartile, the brightest quartile of the data, the LAT targets are brighter than the rest. And the same with the magnitude standard deviation is higher for LAT targets than it's for the rest. However, the post-alert magnitude, if you just take the mean, there's no difference between the two. It is not really a big surprise, as the most of the blue ones, they are blazars, which are supposed to be violently variable sources. Then Michel Dennefeld many years ago asked if I would be interested in looking at the follow-up spectroscopy of Gaias. The initial idea was to search for changing look AGN, but of course I'm observing whatever is available and so on. And in this one, these are lasers, they look changing look, but actually in both cases it's just a featureless continuum, which is the non-thermal continuum goes up and down. In the top plot, you can see magnesium 2 line, which is clearly visible on the low state. High state can't see a thing. And on the bottom plot, the SDSS spectrum shows normal galaxy spectrum, and then our spectrum for Gaia alert, like a high state, it's just a featureless continuum, which is nothing new as such either. But we did find some changing look AGN. The top one is Seifert, looks like Seifert 2, and the bottom one is Liner, based on the SDSS classification, and they are somewhat different based on our data. And so the classification is not written in stone. It's a dynamic feature and shouldn't take it too seriously. And yeah, and then in some cases, well, I had to show some new redshift as well. The top one has no redshift, but there might be galactic absorption lines. That's a radio source. The phone number is down there. And then the other example is based on SIMBAD. It's a catalysmic binary candidate, and based on Gaia, it was candidate QSO. All in all, the candidate QSO classification, I would say that it worked quite brilliantly for Gaias. And then finally, as I'm changing my subject to be a salesman. So if you want to get the observing time from Nordic Optical Telescope, the best way is to be a Nordic or Spanish. And if you are not either of that, then if you have some money, you just buy observing time. If it's very small program, which is like 4 hours or less, then you just send a request to us. And if you have money, then time is yours. And it's less than 200 euros per hour. And if a bit more is needed, then you need to contact the big bosses and so on. And the time, it's either visitor run, TOO, or monitoring, and we are very flexible. We can organized quite a lot of quite different observing programs, whatever is needed for you. And what we have in optical, we have imaging and plenty of filters. Then it's low and high resolution spectroscopy, polarimetry, and in near infrared, it's imaging and spectroscopy. So that was all I wanted to say. Thank you.
Thank you very much, Tapio. Questions, Tapio? Is all these catalogs you showed here, it's pretty amazing, right? The connections to radio sources and then to Fermilab as well. Is it publicly available? Is it published? Is it published?
No, because, well, you can do it and you just do some line of coding.
Okay.
And I did it only 2 weeks ago.
So anyone interested in a quick paper? Lots of citations? Nada.
Hi, I have a question. So for you, I think in the first slide or in the beginning, I think it said that for the VLAS, the survey or the data that you took, the radio one, I think it said it was observed from 2017 to 2019.
Yeah.
So the data is just from that period and you compared it. I mean, the question is, so you didn't check if it was coinciding with the time of the so optical versus the radio, the time difference. Did you take this into account or not? You just cross-matched it based on the coordinates.
So for the radio.
Yeah. So for the matching that you showed
No, I
number.
didn't check the time. It's just the brute force between the two coordinates. That take the number from one catalog and compare it to another number. And it was either yes or no.
Okay, I see. Maybe it would be useful to check to compare, if you have a optical detection before the radio or after, because some sources, I mean, to my understanding, especially AGNs with
Yeah,
flares.
but that's sort of more like a catalog of sources. Then you would have to have I don't think they have a light curves at the VLAS. I'm not sure. I have no idea.
Yeah.
Yes, that's the point. So do you have the timestamp
Yeah, exactly.
from the radio,
Yeah.
which is probably available to some of them because we have it in BHTOM as well. At least one of the surveys we do. But yeah, but it's worth checking definitely.
Yeah.
Okay. Okay, thank you. Any more questions? So when is the next deadline for time? At least, for example, for Spanish time.
No. Well, Spanish time, that I don't know. Somebody said that it's
Now.
quite soon.
This
But the
week.
Nordic time, that's we will put the call for proposals in 2-3 weeks time.
Okay.
So
Okay.
it will be mid-November, I think.
Okay. So I'm desperately looking for some Nordic or Spanish people to collaborate with us because this is a beautiful
Now just
telescope.
use money.
It's much easier to find some friends in Nordic or Spanish countries than find money these days. Okay, I don't see any more questions, so let's thank Tapio again. Thank you.
Thank you.
So now we continue on the topic of the alerts, Gaia alerts, but we switch to microlensing. And now it's going to be very short, tiny session on microlensing. Typically, we have a lot of talks, but not this time. Moritz, the floor is yours.
Perfect, thank you. So my job has been made easy because we had such great talks about Gaia science alerts and microlensing all day. So I just get to show my results pretty much. And just as a short introduction to show you what I'm doing. So the Gaia space mission we talked about all day, this great ESA mission mapping all sky with over 1 billion stars with unprecedented precision. Then the Gaia Science Alerts campaign, which we just heard about, with rapid identification of transients all over the sky. And in this campaign, of course, many microlensing events were found. But now at the end of the mission, we're asking ourselves how many of these events were actually microlensing, how many were classified as microlensing, and are we able to create a catalog of these microlensing events? And so to look at all the microlensing events, to look at all the Gaia Science Alerts events that were alerted on, these 27,000, we can see in the plot that as time went on, the events increased and then stayed relatively constant during the mission of Gaia. And in the red, in the dashed lines, we see the actual data releases. So in the third dashed line is Gaia data release 3, for which we currently have a microlensing catalog, which only spans this very small amount of actual Gaia Science alerts. So by looking at this whole Gaia Science alerts campaign, we're able to create a catalog of events which will only be released in 2030 when the whole legacy survey of Gaia is released. And so our first approach, of course, to find all the microlensing events in the whole database is to look at those which were classified as a U-lens, and then to look at the comments, to look at things which are microlensing candidate or have something like a lens in the comment. Then we run photometric modeling on all 27,000 of these light curves, starting with simple point source, point lens microlensing events, moving on to consider blending in the lens, and then also considering the parallax, so the motion of the Earth around the sun and how that changes the way in which we see the source and the lens during the microlensing event. And then through some statistical and visual validation, we are trying, because this is still work in progress, trying to narrow down onto our final set of microlensing events, which were in the Gaia Science Alerts catalog. So in order to do this, we start classifying them into different groups. And so most naturally, the best or the cleanest group would be events which we can identify based on Gaia data alone. So looking at Gaia 19 ESP, for example, we can see that alone with Gaia data, so the yellow data point, we can see a very nice light curve with a simple point source, point lens microlensing event. Then we have more complex events. So there is enough data during the microlensing event from Gaia. However, the simple models are not able to fit the data, and computationally it's too expensive to run binary lens models for all 27,000 light curves. So these are usually hand-picked, and often already papers for these exist. So for example, for Gaia 16 AEYE, which we've seen a few times today, the binary lens model has its own paper. Then there's events which are only confirmed by follow-up. So here we can see that our models do not work at all, in the sense that we see one data point which is off the baseline and it fits some ridiculous magnification of a perfect alignment of source and lens and says it's a microlensing event, which of course is not displayed in the data because we only have one data point outside of off the baseline. However, looking at other surveys, for example, here from BH-TOM, we can see that the OGL data confirms that in this case, indeed, there was a microlensing event. So by cross-matching these databases like OGL, KMT, MOA, and so on, and also looking at BH-TOM data, we can in fact also find these events which Gaia was not able to find by itself, but were actually alerted in the Gaia Science Alerts campaign. And so here's another example of one which was at the end of the Gaia lifetime. So maybe actually Gaia would have found another data point, but the Gaia mission ended. So it's hard for us to classify it as an actual microlensing event. And then looking again, we can see in this case again, OGL and ZTF are actually able to confirm for us that this was a microlensing event. And then lastly, and this is maybe the less clean part of the data set which we're working on, are events which are uncertain. So we have events, for example, Gaia 24 CTG, for which we don't have any follow-up data. We don't have other surveys which we're looking at it. And you can fit a nice microlensing light curve, but really to say it's a microlensing event is too far of a stretch. Or other events like Gaia 23 BOR, where we are able to fit a nice light curve. We have more than 5 data points in the magnification region, but also we're not back to baseline yet. So it's hard to conclude ultimately that it is a microlensing event, and probably follow-up would be needed to actually confirm this. So here is a small histogram of the events we found in the whole survey. So over 900 events, and the difference in the color is probably the biggest thing to look at. So the green events are the ones which are confirmed by Gaia alone or through follow-up observations. And then the purple events are the ones which will have a large amount of contamination because these are unfinished events or events for which we don't have enough data. And a nice thing we can see is that after 2023, the confirmed events for which Gaia is able to confirm them, or Gaia data alone is enough to confirm them, decreases because many of these events are still ongoing during the end of the mission. Yes. And so here's just a small map of these events scattered around the sky, which I think is a nice complement to the maps we saw before of all the Gaia Science Alerts. So we can see that they are scattered around the whole sky, but also in more dense regions of the Milky Way with more stars, we have more microlensing events as is expected. And so one event which we've been working on a lot with also our collaborators from Lithuania and also Pavel and from Torun and well, in fact, probably everyone in this room, because the whole community of BH-TOM and all follow-up observations is what made this possible, is the event Gaia 20 FNR, which is located quite uniquely for a microlensing event far off the galactic plane and off the center. And it's a very isolated event, which is nice for us to kind of rule out the chance of there being external blending. And so this event was alerted in early December 2020. So we can see in the, this is a plot from the Gaia Science Alerts webpage. We can see the magnitude as a function of the time. And it was alerted very early in the end of 2020. So just as it started to rise in its magnification. But this data alone is not able or is not enough to really classify the event. And so we go to BH-TOM to see, wow, we really have a lot of data. We have, as soon as the black dots are the Gaia dots, we can see that as it starts to rise, then we have the alert and we get lots of follow-up. We have some other survey data to help us and then all the follow-up. So it's a beautiful event to model, lots of data. And to look at it a little bit more structured, I organized it for each telescope. And we can really see, well, a few different things. One, we have a lot of data from small telescopes like RODE, which are essential for this observation. We have observation from 4 space telescopes. So we have Gaia, TESS, WISE, and SWIFT. So we also go from the whole optical range to UV infrared. So we really have a lot of information about this event. And in modeling this event, we see this beautiful light curve is fit with 3 characteristic peaks. So marked by A, B, C. And looking at them more closely, we can see that the data really works well with this model. And specifically looking at the peak A, this is where we have test data, which is really unique because as far as I know, this is the only microlensing event, or there have been no published microlensing events that have test data. And we have test data in 3 different sectors. So at a baseline before the observation, then during this first magnification, and then also, I think a year after the event went back to its baseline. And so we're currently working on finishing this paper about the event. It's a K-type giant at about 3 kiloparsec, which was lensed by rotating binary stars. So what we see on the right side is an on-sky view of this microlensing event with projected into the lens plane. So in the middle, we see the 2 lensing objects, and then the blue line shows the source moving around the lens, like projected into the lens plane. And we can see at these 3 different points, A, B, C, this is where the source comes close to these caustics of the lens and therefore produces this characteristic magnification. And through modeling this event, we were able to conclude that it's most likely an M dwarf binary star that's doing the lensing. And the unique thing also is that we're able to resolve the full Keplerian orbital motion. So in theory, also, this event will be accessible to radio velocity follow-up. And looking at DR4, which is coming up, we can make astrometric predictions because although this event was alerted in 2020, so at the end of Gaia DR4, astrometric microlensing is accessible also years for a longer time range outside of the event. And we can see if, in fact, this model is confirmed by our astrometric data, the astrometric signal is quite unique and bizarre because of the slow proper motion of the source and the lens. There's continuous influence of the astrometric position of the source. And so just to wrap it up, we've been working on a microlensing catalog from Gaia Science Alerts with about 900 candidates, although there is about 400 to 500 which are strong candidates, and then a larger sample of highly contaminated events. But I think the main thing that I could show through the Gaia 20 FNR example is also what was talked about earlier today, is how unique it is that we have these events we're interested in coming from alerts or other kind of science cases. We have these systems like BH-TOM and surveys and other follow-up to gather data. Then we can do our job and modeling it, analyzing it, and we end up with really interesting science results. Thank you.
Indeed, I cannot agree more. Thank you, Moritz. Questions to Moritz. Laurent.
Thank you very much. For the modeling of Gaia 20 FNR, do you take into account that the location of TESS, Gaia, and Earth, that they observe the lens from different places?
Yeah, so this is like the satellite parallax, which we have in microlensing, which can, there's many examples with Spitzer where this has actually helped solve degeneracies in the microlensing light curve. As Gaia is only in L2 and then TESS is also even closer to Earth, the difference is not so great, but yes, it was considered in the modeling.
But in this case, it's not as spectacular as Gaia 16 AYE, where you can actually do see the difference, because this event is less dramatic. That's why it was actually even more complex. I used to say that the Gaia 16 AYE was the most complex microlensing event until we modeled this one.
Maybe
go ahead.
Second question. So when you compare the catalog that has been published in the R3 of microlensing and the rate where the science alert was the most efficient, are these rates similar, or do we find more microlensing events in the catalog, correcting obviously from the observing period?
That's a great question. I'm not exactly sure. I haven't looked at that. I would assume that there should not be any like bias towards some specific times, except that in later observation times, we have more data, more baseline. So we should be expecting to observe more microlensing events, but an actual number, I can't say, sorry.
Well, that's a good point. Well, the main thing is that in the R3, we were able to look at the data kind of retrospectively. So we could detect more efficiently the events from the early of the mission, while during the alerting, we couldn't do that because we didn't have enough baseline, right? So hence, these two data sets are complementary. Any more questions to Moritz? And someone else other than Milena can ask a question. People staring at their laptops, I hope they heard something from the talk and they can ask a question. Okay, Milena, go ahead.
So not that ask the question, I would just give a comment. This Gaia 20 FNR, as far as I could see, the alert was on at the beginning of the March of 2020, so at the beginning of pandemic. So you can see the power of robotic telescopes and small telescopes, because all of the big ones were closed, and here how BH-TOM comes to the stage. And it's
Definitely,
a nice example.
Yeah, and also, thanks for this, Milena, but also it shows that we need a lot of data because especially with microlensing, you never know what's going to happen, right? This event, we thought it's going to be just a simple one, just a blip, right? And then it started rising again, and then it went up again, right? So you never know. So keep observing a lot and very densely. Okay, I don't see any more questions, so let's thank Moritz. Thank you. We stay within microlensing with Michał Kalicki from Toronto. Okay. Use this mic. Okay.
So, good afternoon, everybody. My name is Michał Kalicki from Faculty of Physics, Astronomy and Informatics at Nicolaus Copernicus University in Toronto. And I wanted to say a few words about my recent work titled Spectral Energy Distributions for Gaia Microlensing Events that was supervised by Dr. Paweł Zieliński. It focused on analysis of 1014 objects that are suspected to be microlensing events, and the base probe of the objects were the ones I don't want to repeat after Mr. Moritz, the ones that were found out by CU7 by Professor Berzykowski team. But also we included some of the objects that are currently being found out in the Gaia photometric science alerts by Professor Bruszyńska team. Thanks to her courtesy, we expanded the probe that was published in the 2022 work, 2022 paper in the first ULens. probe. So that summed up to the 1014 objects that we are inspecting. Here's the actually a map that you've just could see. So we see the microlensing events occur all over the space actually, so it's worth looking up not only in the bulge, where of course they are the most common, but everywhere else also we can find something interesting. Here is brightness histogram. So I also want to show you the division, because the probe is quite huge for an individual analysis of each object. So Dr. Zieliński suggested me to divide them into 3 groups, in respect to the quality of their astrometry. Why so, I will explain in a minute. So that's how the 3 groups were created. The one with the best astrometry, marked in green here. So obviously the brightest ones, they had the distance error to distance ratio between 0 and 10%. The second group, the most numerous ones, got the ratio between 10 and 50%, the blue ones. And the last group, the third group, marked in orange, of course, the fainter objects, had the relative distance error between 50 and 100%. We also separated another group. Actually, the objects were included in the 3 groups I've just explained, but they were also set aside for separate analysis. So these were the objects with high RUVE parameter. By high RUVE, I mean over 1.4, which is actually a value that was proposed by the authors of the work where RUVE parameter was explained. RUVE parameter is, of course, the parameter that describes quality of especially Gaia astrometry. So what we wanted to do with the probe. First of all, we wanted to estimate astrophysical parameters of the events, plot them on Azure diagram. But we also wanted to find a simple way to spot some more interesting objects, the ones that are suitable for further research, some infrared excess events, some blends. And yeah, an additional goal was to analyze how the quality of the astrometry affects the results got by the method we used. So hence the 3 groups. We wanted to see how each of the group will perform when using the algorithm we used. And what was it? So that's the part I want to focus on the most, because the talk is actually a crypto advertisement for a program called PySet. It was developed by Professor Ian MacDonald, and it was used for most of the work and turned out to be really simple, really useful, and really comfortable to use. So what does it do? First of all, it collates all the photometric data it can get access to. And that's actually quite a lot of data, because it simply uses the SIMBAT query to find all the catalogs where object desired by the user appears. So you just input the ID or coordinates, and PySet will find any survey that observed the objects. So the problem mentioned earlier with different IDs is non-existent here. You can just use always the Gaia ID, and PySet will cross-match all of the other surveys. Then the data is plotted on SED. Yeah, that's why the name is like that. It's written in Python, and it draws SEDs, spectral energy distributions. So just the photometric data in the wavelength domain. Then the data is dereddened by GTOMO extension grids, but PySet is really open source and really easily customizable. So you can put there any any dereddening algorithm you want easily. And yeah, here's the main part. PySet also includes a database of sterile atmosphere models. And the models indicate some emission curves. So the curves are fitted to the data points. And from that, we get the astrophysical parameters because they are the parameters of the curve. So that's how we got the information we wanted. I don't think I have a time to dive into the diagram, but here you can see how effective is PySet. Some of the objects had to be rejected because I did not have the data was of too low quality. But from 963 objects that were actually processed by PySet, only 26 did not get any fit. So we got results for more than 95% of the objects. So I think it's quite a nice result. And how the results looked like, here you have it. This was actually plotted by myself, but I only used the data outputted by PySet. So we have the data points, we have the fit, we have astrophysical parameters. Here's another example. We can also see the fit, but we can also see the data points, but some of them are like floating above the fit. And I think it's a really nice example of an infrared excess. And we can see it clearly thanks to the fit. So that's about spotting the interesting objects. Of course, PySet is not perfect. Some cases are problematic for the algorithm, as the one in the first one. It's probably some kind of a blend, and some of the surveys separated the two stars, some did not. That's why the points are all around, and the fit is somewhere in the middle, so it's not really reliable. The other ones are just, yeah, the data is are not, the quality of data is just too low, or there is too few data points. But for most cases it does work, and that's how we got the HR diagrams. Here is the one for all 1014 objects, and I think it seems reasonable. Maybe except from the points on the left, which are of a bit too high temperature, and I have my doubts about them. But the interesting thing we can see there is that we have that nice rainbow-like pattern, and the color marks the radii. And looks nice, it looks quite smooth, but there are many points that are standing out from their surrounding. And many of these have that shape of a triangle. And as you can see in the legend, the ones are, they are the ones with high Ruve parameter. So it shows that data points with high Ruve parameter do not perform that well as the others. So yeah, to wrap up, PySet allowed us to get the astrophysical parameters and SEDs for 937 objects. And for most of them, it worked well. But it needs some double checking and need more investigation, especially for the objects with high Ruve parameter. For the objects with little photometric data, it does not work well, but for most of the objects, it is really useful. And we can increase the usefulness by developing our microlensing models, especially for the blending parameter. So I think that makes the method even more promising for the future. I hope you will find it useful too. Thank you for
Thank you very much.
your attention.
Thank you, Michał. Questions to Michał? Moritz. Moritz and Zofia.
Okay. Could you explain some of the high river having anomalous SEDs by them being a blend of two or more sources? Have you looked into that?
What exactly do you want me to explain? I don't think I understood well.
Because high rivers, so anomalous astrometry could have different sources. So it could be astrometric microlensing, but it could be, for example, that we have source confusion or two sources that are blended. And it's puzzling to me that they also have those anomalous SEDs. So if you're looking at those weird SEDs, can they sometimes be explained by there being two sources, or is it not something that you have already looked into?
Yeah, I think I've spot some SEDs like that, but it's not like obligatory. There are so many different reasons for the SEDs to be like that, to just look weird. So sometimes it will be the blending, sometimes it will be connected with high river parameter and some differences in the position. Yeah, it happens, but there are multiple reasons for these anomalous SEDs. I don't think I can say anything more in the topic.
Thanks. Really nice work. I was just wondering, for the distances you used from Gaia, were you using the distance from the parallax or using like Corin Baylor-Jones's distances?
These were Baylor-Jones distances. And again, this is like default PySet setting. And I went with that. But you can always like input, and that's what I think to do in the future to for this anomalous objects to input, for example, distances from multiple sources to just increase the astrometry quality. So yeah, but Baylor-Jones for default.
Did you compare any of your results with some literature data?
Yes and no. I mean, yes, I did. I compared the results with Gaia Apsis ones, and I even have a hidden slide for that. So as you can see, it was compared, but the comparison is like that. My results are completely different than the Gaia Apsis ones. This is actually a graph for temperature. But I do know that Gaia Apsis have some bad press, so yeah, treat it more like please treat it more like a test for that whole PySet program. But I think the method is still promising, even if it did not find its perfect like approval from the...
I will just add to that, because there is a couple of events. It's a handful which we published with Pavel in particular, where we had high resolution spectra, right? So for these, you could do these tests. Just a handful, but these had higher resolution spectroscopy, so probably are more reliable. So that would be worth looking at. Yet another aspect I wanted to ask, I'll use the opportunity I'm a chair, is the time aspect, right? Because because these are variable sources, right? We know, because these are microlensing events. So have you taken into account that the magnitudes, they vary over time? So if you query for your coordinates, does it take into account when was that particular point taken? Because that can screw your SED completely, right?
That's true. That's true. That's why the Gaia the data points from Gaia were often the ones that were I just requested Spicet to omit them because there were often, yeah, you know that these were microlensed, so they were often like highly above
Okay,
the
you ignored
fit.
Gaia measurements because these were taken during the magnification. Okay, cool.
Yeah, in short.
Cool. Right. Any more questions? Yaro?
On the extinctions, these are total extinctions in the direction to the source, or it's just distance dependent? Because that can change, the spectral energy distribution. So if the source is close, then the total extinction to the source would be lower than the total extinction in the direction. So I have no idea what the software is using to change the results.
It uses external extinction grids. So
I don't know if this is distance dependent or just like a total, the galactic dust map or something.
I think yeah, it's some kind of 3D map with like cubic areas of constant extinction values, something like that. I don't really remember. I looked into, but I can't recall.
Okay. Thank you, Michał. Let's thank Michał again. We switch laptops now, so that might take a while. I'll just take this away. Put it here. Okay, don't step on it. Zofia Kaczmarek is going to tell us about looking for black holes with microlensing. You need to connect to Zoom.
Yes.
Share screen. Okay, you're on the screen.
Okay. Hi everyone. I'm Zofia.
Close to the mic.
Okay. Hi everyone. I'm Zofia from. I'm a PhD student at the University of Heidelberg, and today I will tell you about something that's close to all of our hearts as people working on alerts. So classification, and in particular classification of microlensing events to find some black hole candidates. So at first, I will tell you about a classifier I have been working on recently that's purely photometric, and then I will reserve a few slides for telling you what lies beyond with Gaia astrometry coming soon. So why do we even want to do it? What's the motivation, and why is it a good moment to do it? And I will showcase this with a little personal story. So the first ever scientific project I worked on was in early 2016, and it was on whether Gaia would even be able to identify any microlensing events with its precision, with its cadence. And we concluded at an internship that yes, it should. And now in Gaia DR3, this is how many microlensing events we have. So wait for them, they will start coming. So you can see that at any given moment, the sky is not stagnant. There are so many things happening at once. And this animation is over 360 events. In DR4, we already expect thousands, and the generations of surveys that will come after Gaia, like LSST, like Roman, will give us tens of thousands to hundreds of thousands of events. I have no idea why Peppa the pig is on the screen, by the way. So maybe I will just try to put Gaia on again. Yes, so the number of events increases and increases. We don't have enough resources to make people look at all of them and just say, oh, this maybe looks like a black hole, this doesn't look like a black hole. We need some automatized way to process them. While the number of events increases, the number of resources to follow them up and confirm their nature, because as you have heard before, photometry alone can't confirm that your lens is a black hole, remains very scarce and very expensive. We need observations, for example, at the Hubble Space Telescope. And even with those future generation surveys, most events will only have photometric data available. They will not be covered by astrometric surveys, or they will be too faint to have detectable astrometric signal. So that's the kind of statement of need. And now for a little bit of a positive motivation, the microlensing community has recently, about 3 years ago, discovered the first isolated stellar mass black holes. So this is a great step towards filling the stellar graveyard that's for now is just populated by binaries with those microlensing black holes, and see if they change the landscape. So this is why it was a perfect moment to work on our classifier, and we're staying purely in Bayesian statistics. So what we want to get is probability of a lens belonging to a given class for all of the astrophysical classes that we have in our galactic simulation. So we write down the Bayes theorem and we separate it into stuff we can get from our simulation and stuff for which we need our samples from our observed event. And we can show it for microlensing events. Oh yeah, a side note, we do not have to, in this framework, model the detection efficiency of the survey, which is often very hard and very tricky. So that's a good news for us for developing a classifier. If you want to see the derivation of that, you can have a look at the paper by Scott Perkins. So for a microlensing event, it looks like this. And from a light curve, there are just two parameters that are tied to the physics, so what the lens is, how far the lens is, that we can measure from the light curve. The first one is pretty obvious, that's the time scale, so how long the event will last. The second is a little bit more subtle. You can maybe look at the slopes here to see there's a little bit of asymmetry. And this asymmetry is the imprint of us, the observer, changing the line of sight. So that parameter is called the microlensing parallax, pi e. And when we model our event, all the orange bands are samples, and we can put it somewhere in our parameter space, and we can look how similarly it looks to events that we have simulated in our toy galaxy. Those are those candy-colored shapes. And by the way, this toy galaxy is very, very computationally expensive to generate. So we spent days of compute on this. Yeah, so if we break down this space into little points and see if we had an event where we knew exactly the parameters, what it would be classified as, we can gain a little bit of insight on how our space looks like, what is easily classified, what is not. And we can, for example, from this plot, which is from our classification paper, from which all the following plots will also be, we can firstly note that stars are well separated and black holes, which we have here, are well separated. So there is no confusion with other classes, which is great because we're looking for black holes. And the other thing we can note is that there is this weird black blob here that doesn't really look like anything, but is actually one of the most important parts of this classifier. So we wanted to have something called uncertainty quantification, because no classifier can be perfect and no simulation can be perfect. Our classifier is only as good as the galactic simulation it is based on. So there are two causes for the simulation not being perfect. Firstly, we can have missing physics. So maybe there are some classes that exist, but we just don't know about it. Maybe we have primordial black holes or something like this, and we just don't have them in the simulation. But also, even if we perfectly knew what our galaxy was composed of, we'll have sampling effects. So those tails where we just have one or two events. And we have numerical noise, and this numerical noise will cause some artifacts like this. So then if we didn't include this non-class, we would say, oh, something that has those very weird parameters is a better candidate for a white dwarf than those guys located in here. So what we added to the classifier is the way in which it assesses itself, and it assesses how certain it is. When we give it something that's in a region that has no simulation support, it says, I can't really tell you what it is because we have no simulation support. And with that, we have a complete classifier, which we have applied to archival OGL data, and we filtered 10,000 light curves, and we got 23 black hole candidates. So a black hole candidate would be something that no matter what galactic model we use 3 different ones, it says it's more likely to be a black hole than anything else. And 2 notes on this slide. First of all, this is a Gaia Alerts conference. Why OGL events and not Gaia Alerts? So as you have heard, the Gaia Alerts catalog is in preparation. It is a little bit more difficult to model Gaia alerts because of the cadence that is not even and of multiple bands that we have from Gaia and from follow-up. But a similar thing on Gaia alerts is in the works, so stay tuned. Secondly, I would like you to pay attention to this plot and those error bars here. So we can see that the time scale we can pinpoint very, very exactly, but on the parallax and this effective asymmetry, we have a very big uncertainty. So that we will come back to a tiny bit later in a few slides. But before that, I'll just show that we compared it to dark lens codes, so our kind of in-house, thank you, tool developed by Łukasz and the Gaia group. And this is something that needs some extra information because it bases on the galactic distributions of velocities and positions. So we got some Gaia astrometry, we got some extinction, and so on. So we added this extra human effort for the special 23 events. And we found out that the dark lens code says that all of them should be black holes indeed. So all of them have over 97% probability of being dark, and their masses are 13 to 91 solar masses, so they just have to be black holes. So we have great agreement with an entirely independent method. Now is the part where I'm talking about or your favorite science case. So we packed it up into a software package. The primary application is for microlensing events, but you can use it for pretty much any classification case. So all you have to do is have your galaxy, so have your set of mock events where you know exactly what the parameters are and you know exactly what the class is, and your data, so events where you don't know what the class is and you want to classify them. So you can go to GitHub, no class, this is what you will see, this little animation here. And if you would like to use this implementation and its uncertainty quantification and visualization support, which is being developed and will just get better and better, I invite you to have a look into that. We just published it in May. And yeah, so that's it for the photometric part, and now just a little advertisement of the future. So I am not allowed to show you too much of real Gaia astrometry, so I'm very lucky to have this Gaia 16 AYE, which was deemed so important and such a trailblazer that the Gaia Deepak made its astrometry public, even way, way before the R4. So we have heard about it already. You have heard how helpful follow-up was. We will soon have it for all of our events. When we go to astrometry, first of all, we can have straight up mass measurement. We have pi e. As you remember, we had pi e, the asymmetry, TE, the time scale. Now we also have theta e, which is the angular scale of the event on sky. Now, even if our pi e still remains uncertain, we gain something that I call a high signal parameter space. So we can pinpoint TE and we can also pinpoint theta e. And this is an amazing space for classification. First of all, because our events are located in some exact space with very little noise, but also because all the classes beautifully separate. For example, before we couldn't really classify with high confidence in neutron stars, now we will. So this is something we are working on, and let's hope there will be a number in here someday. So yeah, and we have, thank you, because we have events that will very much benefit from this edition of astrometry, and maybe some of those are events that you have followed up and you can recognize. So Gaia DR3 Ulens 001, a candidate for a nearby white dwarf that almost certainly has a lens that's not a main sequence star, and Gaia 18 AJZ, which you can see here plotted in this parameter space. It's very similar to our simulated black holes, but it's also very similar to the only discovered black hole so far with microlensing. So stay tuned for this. So yeah, those are the take-home messages. We have created a new classifier. It's fast, it's flexible. You can put in any simulation you want, and it's ideal as an initial filter. We tested it on microlensing for Ogle, and in the future, we believe that it can optimize follow-up. And as thank you very much for your attention. Those are the links to our classification and software papers. And I'll just leave it here. Feel very warmly invited to Heidelberg for next February. If you're interested in microlensing, we'll be hosting a conference and we'll be very happy to welcome you. Thank you.
Thank you very much, Zofia. Time for one quick question. Simon or Nada? Nada was first.
Hi, sorry. I have thank you for this great talk. I have a quick question for this pop class, the one that you said that you can put any kind of data. Did you test it on something that's not microlensing? Can you confirm that, oh yeah, it does classify it correctly? Or you just, assume that it works for any kind of class?
So have we tested it on something that's not microlensing? Not yet. Why do we assume that it works correctly? Because all that's inside all the math is just purely Bayesian statistics. So it should work for anything where your classes are well separated.
Okay. So, but I assume then it does depend on the data that you provided, that it has to be really well sampled or really clear that it's whichever class you are, right?
Well, so I'll come back to those black hole candidates. So for the data itself, you can sometimes have things that are effectively just upper limits, right? So these error bars in your events don't have to be tiny. I think the real demand would be that what's in your mock galaxy, so what's in your classes that are the basis for the classification, that they are not like this space. Like your entire space doesn't look like this. You don't have a lot of overlap, but you have some kind of a well-defined separation.
Okay, thank you.
Okay, for the interest of time, I suggest we move on, and thanks, Zofia.
Okay.
The last but not least is the very short poster talk by Justas Danavicius, and I just need to very quickly put it on. And then there we go. That's correct.
Yeah.
Is it? Is the one or? Okay, that's a good one. Right. So 3 minutes. So that's the first of the here. So this is the first of the short poster talks. Justas, 3 minutes.
Yes, and I am Justas Danavicius from Vilnius University, and really I like at Observer. I work on few projects. I work with Polish Indina project about lensing, and also I work in another project when we do the cluster research. And this is our command, and few people of us is doing the observation, and few people do the modeling. And our idea is get as most as we can from the clusters from the sky, and get simple the model of that. And the the problem is how to move all sky mass in the clusters. If we want to separate to look what we got from our modeling, and in that case, from that we need some double star. Between really in that project, we just can be user of your time domain, and we use data from can use the data from the double star, or for us maybe will be very interesting to get some to find some small star that we can see really, and it's from method lensing method. It's problem in the modeling. It's the sky. From the model, it's low mass star and big mass star, and it is what slope, how many low mass star we have, and we try to how to use with that problem, and how we can observe all low mass star. Oh, okay. And what we try modeling with, and we did the model. It was the time 0. After some time, we see the cluster going away, going more away, and we decide to investigate not only the clusters, but maybe radius 5 times bigger than clusters, and find all star in that region, which can belong to the clusters, and to know all about the clusters. And it's more disappearing star, and after all, it's no left star in the clusters. If the initial cluster's mass was not big. And we just try compare this modeling and real star. And like it is all. And from that, we try to different initial mass function, initial different cluster mass when we modeling that. And it's okay.
Thank you very much, Justus.
Yeah.
Any quick questions to Justus? I just have one. Can you tell us about this new beast you have there?
What about about
telescope?
Student?
No, the telescope.
About telescope. I think about this telescope you have separate talk from Vitas.
But it's already impressive. And is this one already in BHTOM?
Yeah.
Is it? Okay. Good. Okay. Thank you, Justus. Let's thank Justus again. And I would like to thank all the speakers today, both sessions. And just a reminder about the BHTOM hackathon survey. You all got the links. So we would like to redistribute people to different groups. So make sure you fill in the form. In case you decided to join the hackathon, even though you didn't mark it, so then let us know as soon as possible, ideally today. If you change your mind and you don't want to attend the BHTOM hackathon, and you registered that you do want to, then also let us know, because we need to give the names of people who will be let into the building, because that's going to be in a different building. And anything else? We start tomorrow at 9 local time, right? Which is 10 European time. Paul, do you have any announcements, Anna?
No, me. Yes, we will open the food boxes. Please take as much as you want, because we don't know what we will do with the leftovers otherwise. So eat.
Free dinner. Yes.
And also, please remember to sign the poster. And Lukas, I think you should be the first one to sign it.
Oh, come on. It doesn't matter the order. Okay. Thank you for today, and see you tomorrow. And thank you.